All right. Hello, everyone. Good afternoon. Welcome back. Hope you had a good weekend. All right. Ready to get started? Y'all can hear me okay? Yeah.
Yes, sir.
Okay. All right. So we have a lot to do today. We're going to start chapter 2. This is where things start to get interesting. So, we spent all of chapter 1 talking about the limit and seeing the different types of limits that we can encounter. The most important limit that we're going to be working with today is the limit 0 over 0. But we're going to start from scratch with not a brand new idea. It's an idea that I talked about the very first day. But we're now going to revisit that idea and bring the limit into the game and see how we can finally find the slope of a tangent line or the equation of a tangent line to a curve. So before I begin, I need to get a couple of preliminary algebra things out of the way, things that you should know already, but I'm just going to review them real quick. Back in college algebra, you learn that if you're given 2 points, let's call them x1, y1, and x2, y2, then visually what this looks like is, 2 points sitting here somewhere. I'm just going to place one here. We'll call that the x1, y1. I'll just place the other one here. This is x2, y2. And so if you're given 2 points, 2 distinct points, they're not right on top of one another, 2 distinct points, then you can always draw a line connecting the two, right? So you can always connect these two with a straight line. And that line will have a slope, right? That line has a slope. There's a slope for this line. And there's also an equation for the line. And you should be able to find both of those. And let me remind you how we do it. To find the slope, we use a formula. We usually call it M in college algebra, M for the slope. The slope of that line will always be your rise over run. And in terms of our points, this would be y2 minus y1 over x2 minus x1. So it's just some arithmetic we need to do, a little calculation. And what that comes from is the idea that your rise, right, this rise and this run, the rise is the difference of the y values, and the run is the difference of the x values. And so the slope is defined to be the ratio of the rise divided by the run. Okay, so that should look familiar, yes? You remember that in college algebra, right? Now, the equation of a line, okay, the equation of the line, to do this, we used a formula. It was called the point slope formula. We're going to need to know this formula, all right? The point slope formula looks like this. Y minus y1 equals m times, in parentheses, x minus x1. And I'll also point out to you that to use the point slope formula, we need a point and we need the slope. Okay, that's what you need in order to use this formula. You need to know a point on the line and you need to know the slope of the line, which is why it has the name point slope formula, because you need both a point and a slope. So if you are given 2 points, right? If you're given 2 points on a line, then you can find the slope. Once you find the slope of the line, then you could just take that answer, plug that answer in right here, and then just replace this y1 and x1 with whatever this point is. Now, you could use this point also, but you only need 1 point to have the equation. So we'll just use this one. So that equation there in yellow, you need to know. And the one in green for slope, you need to know. All right. So with that, I just want to add one more little element to this so that when we get to it in a minute, you're not like, what? Okay, so I want you to kind of clear your mind for a second. Let's say that I'm given a function. Okay, f of x is some function. And I'm not even gonna say what it is. Then if I ask you to plug some value a into that function, so I say plug a into the function, then it's going to spit out some answer, right? Something. It's going to spit out an answer. And that answer will be the y value. Okay, so how far up you go, or down, it could be negative. So the height of that point would be f of a, right? And if you looked at that point as an ordered pair, the x coordinate would be a, and the y coordinate would be the function's value at a, which again, we don't know what it is, but that's what the y value is. So what I'm trying to get you to see is this would kind of be like the x1, and this would kind of be like the y1 from what I was explaining here, right? At some point, this was just two arbitrary points, but that point could come off of a function, could be a point on a function. So that's another way you could look at the x and y coordinates of that point. And then if I gave you another point, let's say I gave you the point, I don't know, I could call it B, I could call it C. Let me just call it X. Okay, I'm just gonna call it X. Then whatever happens when you plug X into the function, it's gonna spit out an answer, and that will be the function's value at X, whatever it is. So again, as an ordered pair, this looks like X, f of X. Is that clear? Any questions on that?
Wait, would it still, if we had that as a second point, would it still be, oh, never mind. So that would be x2, but
Yeah, so if we were looking at this as a second point, then we would call this x2, and this would be like the y2. But see, the thing here now is that it lives on some curve. Oh, shit, I missed it. Right? So these are just two arbitrary points on a curve, where here I just gave you 2 points, and we weren't even talking about a function. We were just saying, hey, here's 2 points. How do you find the equation of the line? That's it. Okay, you all ready? I think that should be enough for us to start.
okay.
All right, so chapter 2 is called derivatives, all right? And if you ask a Cal 2 student what Cal 1 is about, most of them are going to tell you it's about derivatives. So this is a core chapter for this class. And you've probably heard this before if you've talked to someone who's taken Cal 1 and said, oh, it's about doing this thing, taking derivatives or whatever. So this is the chapter where we get into this. The first section is called derivatives and rates of change. All right, now I know you can read this, but I'm going to go through this. We now study a very special limit. Okay, so we've looked at all types of limits. Limits that give you 0 over 0, infinity over infinity. Sometimes we get like a fixed number over 0. Last class we did infinity over infinity. We did infinity minus infinity, and we were looking at all these different like special. We've been looking at all of these different special forms that we can get when we take limits. Today we talk about a very, very special limit. Okay. It's one particular type of limit that we can encounter that will eventually lead us to basically the major idea of what Calculus 1 is about. And that limit, we're going to have a name for it. It's going to be called the derivative. And it's going to be what helps us find the tangent line to a curve. We can also find velocities of moving objects. Using this, we can find instantaneous rates of change of basically any function, which I'll explain later as we get into this more. But this is, again, this is a major thing here. And when we're all done with this, and we understand the idea of the derivative, then we can apply the idea of the derivative to some very difficult problems, word problems, okay? That I think I gave you one where we were trying to connect 2 buildings with fiber optic cable. Remember that? I said, hey, you know, how would we minimize the cost? Those types of questions can be answered, but you have to have the derivative. Without the derivative, you can't do it. Okay, so first we look at the idea of a tangent to a circle, which all of you, you know, from your past, I think, I'm not gonna say all of you, most of you know what I mean when I talk about the tangent line to a circle. So if I give you a circle and I give you a point on that circle, then sorry, if I give you 2 points on a circle and connect those 2 points together, that's called a secant line. But if I slide that blue point over across the circle, see, we still have a secant line right now because it's connecting 2 points on the circle. If we slide that blue point right on top of the black point, we get what's called the tangent line. And so it just like barely, it just touches the circle at one point and kind of balances on the circle, right? So again, most of you have seen that idea before. Now, when we talk about the tangent line to a function instead of a circle, we have to be careful because the definition is a little bit different, because one way you could define a tangent line to a circle is to say it's a line that hits the circle at only one point, right? So think about this. If I have another line that goes through this black point, if it touches at another point on the circle, then it can't be the tangent line. It can only touch at one point, and that's what makes it uniquely the tangent line. But on a graph, it's a little different. So let me show you. Let's say we take this graph and we take 2 points on this graph, just like we did on the circle, and we start sliding the blue point over to the black point, but keeping the blue point on the curve the whole time. You can see as I move it, you see the blue line, the slope is like wobbling all over the place, right? Like the slope here is positive, and then the slope is negative, and now it's still negative, but it's starting to flatten out. Now the slope is positive, and eventually, right, I get closer and closer and closer. You can see that that line is starting to like become this idea of a tangent line, right? You can zoom in on this so you can see I'm zooming in now. I'm trying to slide that point right on top of the other one until I get to this magical place right there. So now I have created the tangent line. Now, what makes this a little different than the circle is that this tangent line might hit our graph somewhere. So if I were to extend this graph up like that, right? Maybe it does that. Then can you see, I don't have green here. I can't do this with green, so I'm gonna have to do it in, I'll do it in blue. This tangent line, do you see that it would eventually hit the graph again? That's not important to us. When we're talking about a tangent line at a specific point, we're talking about this blue point. It's tangent at this blue point because it kind of rests on that curve in a way that it's just touching that curve at one point right there locally. We don't care about what's happening on the bigger picture. Is that all right? Does that make sense? Questions?
So if it's a circle, it has to be touching only one point. If it's
That's
a
right.
function, it's okay because we're just looking at the
It's
spot
okay.
where this.
Yeah, it's okay what's happening in other places. We're looking at what's happening at a specific point, and then it's like it's almost kind of like the circle in that little area, that little neighborhood that we're looking at. Do you all agree that this tangent line appears to be unique, meaning there's no other tangent line at that blue point? Like, I don't think someone else could come draw me another line that would kind of be behaving the same way. As I move that second point closer, like that tangent, that line right there is not the tangent line. And there seems to be like, it seems to be like that blue line is like headed to a specific place, and there's really only one place it can be, and that's there.
Which
Right.
is a limit. Oh my
Like,
God.
it's not like that. Like, you can't say, oh, well, that could be a tangent line also. No. Because when you zoom in, you have to just be touching this point. And as you move away, you shouldn't be touching the graph, okay? All right, any questions? I'm going to proceed. Any questions on the concept visually of what the tangent line is? All right, so this is what I covered already when we started class. We've already seen from the two examples above that to get the tangent line, we must start with some point on the curve. So we started with this blue point. We started with that black point. Start with some point on the curve. Select some other point different from our first one. So that's this blue point. And then draw the line between those 2 points. So that would give us this secant line. Then slowly move the second point closer and closer to the first point. When the 2 points are on top of one another, we get the tangent line, right? That's kind of like in words what we were doing to get to that tangent line. Now, what does that mean algebraically? Okay, so this right here is what I already talked about. We've already been through this. I'm not going to go through this. If you're given 2 points, we can find the slope, rise over run, right? And the equation of the line is the point slope formula. So I'm not going to cover that. What I want you to see is that if someone gives us an actual function, let me make this bigger. So if someone were to give us an actual function, okay, for this particular example, the function that we're looking at is this right here. Okay, f of x equals 3x cubed minus 5x, right? If I was interested in finding the equation of a tangent line, right, then what I would first start doing is I would have to select like a starting point. Like, where do I want to be looking for the tangent line? So maybe right there, I want to know, okay? Now that point, it looks like I got that point by plugging in. It looks like -1 got plugged in. So I plugged in -1. So that point has as an ordered pair, -1, f of -1. That's what we were talking about earlier. If you plug in -1, the y value will be the function evaluated at -1. And that happens to be this. I already did the work here. It's -1, 2. So if you plug -1 in here, you're going to get 2. So we start with that point, okay? And my question is, what is the equation of the tangent line at that point? Okay, that's what we want to get to. So what we do next is we pick another point, any point we want. Okay, so there we go. I picked this point. Looks like the x coordinate is 1. Okay, I just picked that point. And we know we can draw a line between those 2 points because we know from college algebra that if you give me 2 points, I guarantee can draw the line between them, right? So everyone in this class should be able to get the equation of this line right here, because you have 1 point here and you have the other point here. And so you just do what you did in algebra, right? So we would just, figure out rise over run, and then we get the equation. I'm not going to go through this work, but I'm trusting everyone in here given 2 points to get the equation of that line. So what we want to do now is start sliding that blue point closer to the black point so that we can get to the tangent line, right? But what this note is about, and I want you to really think about this, is that as long as I start with the black point and give you a blue point that's not on top of the black point, everybody in here should be able to find the equation of the line through those 2 points. As long as they are distinct different points, you should be able to do it. The question is, what happens when we slide it and put them on top of one another, right? What happens? So let's continue. I'm going to go through here. All right. So how do we obtain the tangent line from the secant line? Make this big here. So we start with the first point on a function. And in this picture that you're looking at right now, this is just an arbitrary function. I'm not telling you what the function is. Okay, this is just some arbitrary function. And I want you to say to yourself, okay, right here, this is some value A. All right. In the previous example, it was -1, but here let's call it A. And so we know that the ordered pair that goes with that point is AF of A. Now we pick our second point, some arbitrary value over here, so wherever you want. And for that one, let's call this arbitrary value X. And so if you plug X into the function, the Y value is F of X, right? Now, if we draw a line between those, okay, can somebody tell me what the slope of that line is? I need someone to tell me what is the slope of the line, the secant line that I just drew.
Just the like A minus X over F of A over F of X.
Other way around, you got it backwards. You got it backwards. So remember, the slope is y2 minus y.
Oh, yeah.
2 minus x1. So for us, this would be, let's see, y2, the second point's y coordinate is f of x. So this would be f of x minus the y coordinate off the first point, which is f of a, over the x coordinate on the second point, which is x, minus the x coordinate on the first one, which is a. And this would be the slope. I'm going to put in a subscript SEC. This is the slope of the secant line. You all agree with that? That would be the slope of the secant line. If somebody told me what the function was, I could do this. Right now, no one told me what the function is. So this is almost like a general formula, isn't this? This is a formula that would give you the slope of a secant line on a function between the x value a, I'm sorry, yeah, the x coordinate being a and x. You with me? Okay, so here we go. Now what we'd like to do is we'd like to take that second point and start sliding it over, 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 until eventually we get on top of the other one. And then we have a problem, right? Because what happens when we put the 2 points on top of one another? What is created here? What does our slope of our secant line look like now?
0.
0
It's
over
at
0.
Yeah, it's this, they're the same exact point. So we get 0 over 0, which is undefined. Okay, it is undefined. However, if I were to just move that second point just slightly away, right? Once I put it on top, we have a problem. But if I just get it really close, like real close, like a limit, okay? Like a limit, we want it to get real close to it without actually getting there. That's what the limit was all about. Then what we can ask ourselves is, what does this turn into? Like, instead of getting that, what does that limit approach? Okay. So we have the problem, right? We get, if we try and find the slope of the secant line and we have the 2 points on top of one another, we basically have 0 over 0, which is undefined. So the workaround, the way we get around this is very simple. We're just going to take a limit, all right? So I'm not going to read through this whole thing, but here it is. This is the big definition right here. The slope with a subscript tan, this means the slope of the tangent line, is exactly the same thing as the secant line formula for slope. But we're not going to let, we're never going to let x actually go, like, become a. We're going to see what happens when x approaches a. So think about this intuitively. When we take a limit and I'm saying let x approach a, what's happening there visually is that I'm taking this second point. What was the x coordinate of the second point? What was the x coordinate of this? What did I call it?
X.
It was
Oh,
x,
x,
so
right?
f of x.
And then this one over here, this was a, right?
Mhm.
And so what I'm doing is I'm trying to let this x slide over and become a. I'm trying to let x become a. That's what happens when you start sliding this over, right? That x coordinate is marching its way along, getting closer and closer to a. And then what's happening up here is that we know if we ever get to a, we're going to get 0 over 0, but in the limit, we'll never get there. We'll get just really close, right? Really close. Infinitesimally close.
I have a question about it though. With the when it asks, whenever we get like the actual questions for it, are they going to tell us from which side they want the derivative? Because isn't that going to be important? So like from the left side, like, because
That's a
it
great
would
question.
change.
That's a great question. Is it, so when we need this to actually work from both directions, right? So for us to be able to find the slope of a tangent line or equation, we need the limit to exist from both sides. Now, fortunately for us, we won't have to worry about that too much because all the functions we're going to deal with in this class are going to be continuous and nice. So the limit from the left and right should be okay. Should match. Good
Oh,
question.
so no, but it wouldn't change it like just even like the littlest bit because it's coming from the left side or the right side. It wouldn't matter from which side you would choose it from.
Let me see. Hold on. Let me see if I can edit this code real quick. I think I should be able to edit my code real fast to change this.
You gotta remember the limit. It's approaching a value. So top bottom, it's continuous function, meaning if it's continuous, it has to be approaching the same thing because it has to be a real limit.
That's
So
right.
But
But let me try and address this slide second point, blah, 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 -1. Let me go to negative. Try and rerun this code. I don't know what's going to happen here. It should work, but. Okay, so first point, that's I like to call that point our base point. Okay, that's like the anchor point. That's where we want to find the equation of the tangent line. The second point is arbitrary because we're going to be letting that thing head towards the other one. Okay, so the question Brian's asking is, there we have our problem, right? That's where we have our problem. But see from the other side, do you see that we're still approaching the same line? Like the slope is still approaching the same thing.
it wouldn't be like, wouldn't there be like even the slightest bit of a different answer? If
Well,
if you would be right on the other side and then one would be right on the other side.
yes, you're right. But are they approaching the same thing?
Yes.
That's the key. I agree with
Okay.
you that from the left side, your slope might be a little bit different than the slope from the right side, but they are both headed towards the same value.
Okay.
The pitch of the line, they're both headed to this one number and not two different numbers. It's kind of like if you take just a very simple limit, like think about it this way, Brian. If I just were to ask you what's the limit as x approaches 0 of x itself, okay, then if you were to graph that as a function, here's what f of x equals x looks like. If I approach it from the left, I'm headed towards 0 through negative numbers. From the right, I'm headed towards 0 through positive numbers. They are both headed to 0, aren't they? Some of them are some of them are negative, some of them are positive. From the left, it's negative, from the right, it's positive, but they are both headed to 0. And so what we say is that the limit is 0.
Okay.
Difference, the fact that one side is positive and negative doesn't matter because they're both getting smaller and smaller and smaller and smaller and smaller. I hope that that's okay, Brian.
Yeah, I was just.
It's a good question.
Well,
What's
right, 'cause-
happening here is that with questions like that, what's happening is that the preciseness of our definition starts to have some flaws because I'm saying close and close. And what does that mean? And I told you I want to avoid that because it just gets into a whole different level of math that we don't need to continue. So I'd be happy to entertain more of that in my office hours. Okay, so we have this new idea that we're gonna, in order for us to find the slope of the tangent line, what we're gonna do is we're gonna take that same formula that we just had for the secant line, and we're just gonna change it by taking a limit of it. Now, what I circled here, you should recognize that from college algebra as the difference quotient. Do you remember studying something called the difference quotient in college algebra?
Yeah, X.
This is actually it. And the reason you study that in college algebra is because they know in Cal 1, you're going to need to take the limit of it. So if you can't figure out the difference quotient to start with, you're going to have trouble with the limit. So, okay, now, it is possible that this limit doesn't exist. It is possible. So if the limit does exist, then it's just going to give you the slope of the tangent line. Okay, let me see what I want to do here. I think I want to do an example. Okay, let's just do an example. I want us to find the slope. We'll start with slope of tangent line to the curve f of x equals x squared plus x at x equals 3. All right, so I like to always back this up with pictures to make sure everyone here knows what we're trying to do visually. We're looking at x squared plus x, and we are going to the what was it? X was 3. Is that what it was? Yeah. So x squared plus x. Here's x is 3. So if we plug 3 into that, what would we get if we plug 3 into that function? 12.
12.
At 12,
Right?
yeah.
Okay. So if we go and we look at this graph and we look at this point at x is 3, here's 12, right, comes out, then I would like to know that the tangent line to that curve, what is its slope? So just by looking at it, do you all agree that that our answer should be a positive number for the slope because it's pitched up?
Yep.
And it should be a pretty big positive number because the larger your number is, the steeper your line is. So this line, this tangent line should be a pretty big positive answer. Let's see. That was just to show you visually what we're doing. All right, so how do we do it? Well, the slope of the tangent line, by definition, okay, the way I just defined it, is the limit as x approaches a of f of x minus f of a over x minus a. Now, in this particular problem, what is a? So what's that anchor point? Where's that base point that we're interested in?
312.
So a is the 3, right?
Right.
A is the 3. The 12 will come into play, but the a is the 3.
Right.
So even though it says x is 3 here, I know it's confusing. That's what the a is. Again, go back to the picture. The whole idea here is that we're picking an anchor point that we're going to start at. This point here is our a, right? That's the a we're starting. So for us, it's 3 because that's what the problem says. Find the equation or the slope of the tangent line at 3, at x equals 3. Okay, so what I'm going to do now is I'm going to say slope of the tangent line then for this particular problem would be the limit as x approaches 3 of f of x minus f of 3 over x minus 3. So I just replaced all my a's with 3's. All okay with that?
Mhm.
And now we need to plug in, okay? So let's plug in and let's figure out what these things are. So let's start with this, f of x. Well, do we know what f of x is?
X squared plus x.
It's x squared plus x. Okay, that's f of x. Then we want to subtract from that f of 3. So f of 3 is what we get when we plug 3 into the function, which we said was 12, right? So that's 12. That's this part. And then we want to divide all of that by x minus 3. There's no work to do on the bottom, okay? Because x minus 3 is x minus 3.
Then could we factor the numerator and cancel out then?
We can. Now, do we need to, though? Well, look, take a step back. What are you looking at? You're looking at a limit, right? And what do we always do for limits?
Plug in the
Plug in,
value
see
you're
what we
approaching.
get, right? So let's see what we get when we plug in. If I try and plug into the top, I'll get, let's see, 3 squared is 9 plus 3 minus 12 all over 3 minus 3. And so now I'm getting 0 on top, 0 on the bottom. And that's bad, right? So we need some algebra. So if we do some algebra here, notice I'm going to keep the limit here, limit x approaches 3. The algebra on top, I can factor. Fortunately for us, the top factors. Right? X plus 4, x minus 3. The x minus 3's cancel. Now all you have to do is let x go to 3. And what's your answer?
7.
7. So we can't overstate how big of a deal this is right here, okay? Like what we just did, and it's nothing crazy. I mean, it's just a limit. It's not a hard limit. But what we've done is we've said that if you were to look at this graph, okay, and you were to go to the x value 3 and go look at that point, I can tell you right now that the slope of that tangent line is 7, right? That's what I can tell you. And that kind of matches with what we thought would happen because that's a pretty steep looking tangent line here, right? Now, let's add one more element to this. Let's now take this and let me add to this question. Now, find the equation of the tangent line. At x equals 3. Okay, so what do you need to find? What do you need in order to find the equation of the line? Well, a point and a slope, right? Point and a slope.
Mm-hmm.
So do we have a point? Do we know what point we're talking about here?
We use our anchor point at 312.
Yeah, we use our anchor point. So we need a point and a slope. Now the point we know is the point 312. We knew it was 312 because we plugged in 3 a couple of times now, so we know what happens. And the slope we found was 7. And if we just use the formula y minus y1 equals m times x minus x1 from college algebra, and remember that the 3 is the x1 and the 12 is the y1, then we're in business, right? This is our m. So this should become y minus 12 equals 7 times x minus 3, which is y minus 12 equals 7x minus 21. And then y equals, let's add 12 to both sides, 7x plus 9, or minus 9. Any questions? What should we do with that answer right now? What would be kind of cool to see right now?
Plug it in on like a GeoGebra thing and see the line.
Yeah, let's go graph it. Let's
Why
go
use
graph it on
GeoGebra,
this
but
graph.
use Desmos.
If I graph y equals 7x minus 9, we should see a line that goes through that blue point and is tangent to the curve. There it is. See that? Zoom in on it. I'll zoom out so you can see it. That is our tangent line. It's tangent to this curve at this point. So again, take a step back. Think about this. Walking into class today, if I had given you this function, x squared plus x, said, hey, everyone, that's a parabola from college algebra. If I would have said to you, hey, go to this point, x equals 3 on the graph, and tell me the line, the equation of the line that goes through that point and is tangent to the curve, you would probably have thought of that and just been like, I have no idea how I'm going to do that, right? Do y'all see that it's not, there's not a lot that you, I mean, there's a lot you have to do. You have to be able to do a limit, and then you just use a college algebra formula and you're done. So it's really amazing how simple it is, but at the same time, how much like you can accomplish with it. Any questions? Sure, let's do another example. Find equation of tangent line to the function f of x equals 1 over x squared at x equals 2. So I'm going to graph it. There's the graph of that function, 1 over x squared. And I wanted to know what's happening at 2, right? At the equation of tangent line at 2. So if you plug 2 into that function, what would you get?
1/4.
1/4. Good. Okay, so see that point right there? I would like to know the equation of the line that would just go through that point and be tangent to the curve. Again, it seems like this might be a pretty hard thing to do in general without any limit or calculus, but we can do this pretty easily. No, I'm not going to say easily. In theory, what we need to do is not hard. Sometimes the calculations can become tough. All right, so I want the slope first. Let's start with the slope of the tangent line. And this should be the limit as x approaches. Okay, I start calling on some people here. Is Nathan here today?
Yes.
Nathan, are you following okay?
Yeah.
Okay, so what's a for us here, Nathan? What's the a we're using?
Let's see. The x at the x value.
Yeah, so what is it for us here?
2.
2, right? Okay, sorry, I didn't.
I didn't get to finish writing down the whole problem.
Oh, you thought I was just writing this down, the formula?
No. I just forgot to finish writing down the at x equals 2.
Okay, got you. Okay. So I'm using this Nathan's using this formula and realizing that the a we're approaching is 2, right? So go ahead, Nathan, tell me what this limit, just tell me what everything else I'm going to write here is.
So it's going to be x, the limit of x approaching 2, and
Okay.
then it's going to be 1 over x minus 1 over x squared minus 1 over 2 squared minus x over x minus 2, right?
Perfect. Okay, now let's make sure everyone else understands what you did there. Does everyone see that 1 over x squared is just f of x, right? That's just this part of the formula. And then f of a is this, but remember, a is 2 here for us, right? So you're plugging 2 into the function that's given. 1 over 2 squared is 4. And then the bottom is just x minus a. For us, again, a is 2. So the key is to know that a is 2 here. Everyone agree? Okay, good. Brandon, are you there? Brandon?
Yes, I'm here.
Okay, hey, Brandon. You following okay?
Yeah.
Okay, so Brandon, you have a limit in front of you, right? So what's the first thing you do when you have a limit?
The first thing when I have a limit.
What do you always do when you have a limit?
Well,
No one help?
You plug in
Plug in
what
the
value
number.
you're approaching.
Plug in, just see what happens. Like, just let's replace x with 2. Okay, let's just replace x with 2 and see what we get here. So Brandon, if we replace x with 2, what do we get on top?
1 over 4.
1 over
Minus
4
1.
minus 1 over 4 again, right?
Then I get 2 minus 2.
And then we get 2 minus 2. So this is looking like it's going to be 0 over 0, right?
Mm-hmm.
And since we're getting 0 over 0, this is not good. That means we're going to need to do some algebra, right?
Yes.
So are y'all seeing why we spent all that time in chapter 1 doing limits? Because you can't do this next step if you can't do those limits.
Mhm.
Okay. Brandon, I'm gonna give you another shot here. Brandon, if you had to start working out this limit, do you have any sort of instinct as to how you would first start trying to do something to make this not be 0 over 0? Is there like, have you developed an instinct for what you would do on this one?
I would try to get rid of the 1 over x squared
Okay, so how?
by multiplying it, the numerator and denominator.
So what I think you can correct me if I'm wrong. Are you thinking of what we were doing when we were getting infinity over infinity, and then we would come in with something on the top and bottom to make the highest power of x go away? Is that what you're thinking?
Mm-hmm.
Okay, so that you only do when you have infinity over infinity. We don't have that. We have 0 over 0, right? So when you have 0 over 0, this is a different technique. You do not want to do something like this. So this is what look, everyone, this is why we're here, right? Is to make sure that we understand what path you go down, right? Because it can be very confusing. You start doing things that you did in the previous section, but this isn't necessarily connected to what we're doing here. So, so Brandon, when you have 0 over 0, and you see here a bunch of fractions within fractions, my advice to you is to try and combine these two fractions together. Put these two together, which means get a common denominator. That's the procedure that I normally go after. So I would multiply this by 4 over 4 and this by x squared over x squared. That way, both of these have 4x squared on the bottom. Now, when I do that, I'm going to have this 4 over 4x squared. And then when I subtract from that, I'm going to get x squared over 4x squared. So I'm going to subtract x squared over the common denominator, all of that over the x minus 2. All right, Cody, I think you're up.
Okay.
So you okay up to that point, Cody?
Yeah, I'm good to this point.
Okay, so what now?
I'm assuming we're gonna have to try to clear the x minus 2, so maybe multiply the top by x minus 2 over 1.
Okay, so like, you'd have to do it on top and bottom.
Oh, yeah, okay, yeah, x minus 2 on both.
So, Cody, squint your eyes and look at this expression. There's something here. Just take a minute to look at it. There's something here. Do you see something special? You don't like the x minus 2. You already said you don't like this, right?
Mm-hmm.
Look at the rest of the expression. Do you see something?
Difference of squares.
Yes. Good. Y'all see that? Look at the numerator, 4 minus x squared. That can be rewritten as 2 plus x, 2 minus x, because that's what happens to a difference of squares. And Cody, that's actually really good, but not quite perfect. Do you see, Cody, that this x minus 2 and this 2 minus x are really close to one another?
Right, they're close.
They're close. They're not exact, so I can't cancel them. But Cody, what can you do to make them cancel? Remember we did this? Just a quick little algebra thing we can do to make them match.
Multiply -1.
Or factor. I'm going to do a factor.
Or factor
I'm
out the
gonna factor -1 out. I'm going to take a -1 out of this parenthesis, which makes it a -2 plus x. So look, everyone, what I'm seeing is that this and this are almost exactly the same. They're almost exactly the same. They're just off by a sign. So if I pull a -1 out of the top one, or I could pull it out of the bottom one also, it doesn't matter which one. If I pull a -1 out of just this factor, then I get this. That's all over 4x squared, but that's all over x minus 2. And Cody, do you see that those two now can cancel?
Right, you can.
I know that the order is backwards, but they're exactly the same expression, right? Negative
Right,
2
they are.
plus x is the same as x minus 2. Okay. So let's see where we are. We have not taken the limit. We just did algebra. We have on top, I'm going to write it this way, negative 2 plus x over 4x squared. That's the only thing left on the bottom, right?
Right.
Okay.
And now we can plug.
Yeah, now just let x go to 2. Let's see what we get. No more limit, right? I'm letting x go to 2 now. So I get negative 2 plus 2 over 4 times 2 squared gives me negative 4 over 16, which gives me negative 1/4. This is the slope of the tangent line. What do you think?
Yeah, yeah.
Okay. Now, have we answered the question? Have we answered the question for the problem here?
No, we just found what we needed to answer the question. You need slope
Uh,
first.
That's right. We want the equation. We've only found the slope. But the equation should be the easier part, because to do the equation, all you need is a point and the slope. The slope we just found to be negative 1/4. Cody, what's the point that we're going to use here?
We're gonna do 2 and then 1 over 4.
2 and 1/4. So everyone, that comes from the fact that we're plugging in 2 into this function and getting 1/4. So that's our point, that's our slope. So we're going to do y minus 1/4 equals the slope negative 1/4 times x minus 2. There we go. That should be the equation. I will clean it up. Let me clean this up. So when I distribute through, I get negative 1/4 x, and I get positive 1/2. And then I need to add 1/4 to both sides. When I do that, when I add 1/4, I should get 3/4 when I add it to 1/2. And that should be the equation of the tangent line. Are there any questions while I'm letting people copy this down?
Well, so if y1's -4, shouldn't it change to y plus?
Y1 is positive 1/4. I think you're confusing y with the slope.
Oh, yeah, you're right. Never mind.
Yes,
My
okay.
bad.
No, I'm glad you said that, because I was actually going to say that to be careful. That, make sure that you be careful, because we had 1/4 in both of them. One of them was negative, the other was positive, not to confuse the two. All right, we should be able to check this answer, because I should be able to go here and graph that line now. So y equals negative 1/4 x plus 3/4. Yep. I think we got it. Would you agree? We got it.
Wait, I'm having like a brain slip all of a sudden. Where did we get the 1/4 from again? I know I answered earlier, but now I'm like questioning where I got it.
Where did we, oh, the 1/4 for the y coordinate here?
Yeah.
That's f evaluated at 2.
Oh, right. I was looking at my notes. I
The
was looking at
original
the
function
old.
evaluated at 2.
Yeah, I looked at
So
the old
that's
function.
1/2 squared.
Right, got it.
All right. All right, now I'm going to give you something to work on. We're going to do a little breakout room here. We're going to put you on groups. And what I like, yeah, okay, you ready? I'm going to write down 2 problems and put you in groups, see if your group can get through both of these. So I want equation of tangent line to the curve f of x equals x cubed at x equals 3. And then that'll be problem number 1. And then I want for 2, the equation of the tangent line to f of x equals the square root of x plus 1 at x equals 8. Take a moment to do that. I'll make the breakout rooms. So the breakout rooms are just, I'd like for you to talk to one another. If anyone has the ability to share their screen and draw on a board, you can, whatever y'all want to do. I just think it's too much to have everyone in one room if you want to talk to someone. So there's going to be 3 to 4 people. You think that's good for y'all? 3 to 4 people in each room?
That'll work.
Yeah, okay. So I'm creating it, and as soon as you write the problems down, you're free to join. And we'll see what y'all can do in about, I don't know, 10 minutes, 15, maybe 12 minutes. See how far you can get. Help each other out. So when
Just
you're
a quick
sorry, I
question.
didn't open the rooms. Sorry. Okay, there you go.
Will you be popping around?
Yep. You can ask for help. You can raise your hand. I'm going to try and jump into the rooms.
Okay.
I'll cycle through. Yeah. Samuel or Brandon, are y'all here?
Oh, sir, this is just
Oh, it's a different device.
yeah, it's a different device because my computer doesn't have a camera, so I'm using my phone.
Okay, cool.
So
Yeah,
my
that's
teammates could actually see me. That's why I backed out of one of the.
okay. Just stay here then. Samuel, are you there? Samuel, are you there or no? Okay, I think everyone's back here. All right. So, who would like to volunteer the final answer for number 1?
We got y is equal to 27x minus 54.
27x minus 54. Is that what you said?
Yes, sir.
Okay, I've already graphed it here. So let me do this. Y equals 27x minus 54. Looks right. That looks good. So what do y'all think? Do I need to go through the work on that one? Was that okay?
That's what I got to.
It was pretty good. Yeah, I got it.
Okay. Difference of cubes formula, you needed that to be able to factor. Other than that, everything should have worked out pretty clean. How about the second one? Any groups get that one?
I got y equals 1 over 16 x plus 5 over 2
1 over 16 and then x and then
X.
what?
plus 5 over 2.
Plus 5 over 2. Okay, we'll see. Y equals
Did I?
that looks like it might be off.
Yeah.
Do you see that? See, you got a line. It does go through that point, but it doesn't look like it's tangent. Seems like there's something off here.
Can I go over my steps to see where I went wrong?
Yeah, let's go through that one. I think because not
Okay.
everyone got to that one. Okay, so you set up the limit first, right?
Yes, sir. So
Limit
I started off with the square root of x plus 1 minus 3, because 8 plus 1 is 9, square root 3, and then over x minus 8.
Okay, is everyone clear on that step? That's the first, that's the initial setup of everything using the formula right here. Pop that in here real quick. So the f of x is just this. The f of a is that part right there, because when you plug in 8 into this, 8 plus 1 is 9, square root of 9 is 3, and then over x minus 8. Okay, what did you do at that point?
At that point, I squared both the top and bottom to eliminate the square root.
Okay, that's the
So-
problem.
Okay.
You can't do that. So I don't know if you remember, we talked about this. When you have a limit, you cannot just arbitrarily square the top and bottom, because then you change the expression completely. You can only square things when you have equations. You can square both sides. So does anyone know what we can do?
Conjugates.
Square root to the
Yeah, come in with the conjugate. So what we're going to do is multiply the top and bottom of this by 1. But the one that we're going to choose is the conjugate of the top. So it becomes square root of x plus 1 plus 3 over square root of x plus 1 plus 3. And that's because when we were going through this, I said to y'all, when you see square roots, start thinking conjugate, right? Because most of the time it works out. So we have to FOIL out the top. And do y'all remember what I told you about the bottom, what to do on the bottom?
Just leave it.
Just leave it alone. Just leave it alone. So let's FOIL out the top. And I'm writing this limit. Notice I'm continuing to write limit. I don't, sorry about
Why'd
that.
you put infinity? Okay, there we go.
My 8 went to sleep, I guess. So, all right, so we've got this, and now let's do our FOIL. So here to here is x plus 1. Do I need to do the middle terms? Do I need to multiply out the middle?
Nope.
No, because they're going to go away. That's the whole idea. And then so the only thing left is the last terms. Negative 3 times positive 3 is minus 9. And then over the x minus 8. But that still needs to multiply by the square root of x plus 1 plus 3, but I'm not going to do that. And the reason I'm not going to do that is because my numerator is actually going to turn into x minus 8, And that is going to cancel out. So limit x goes to 8. Okay, what's still left on top?
1.
A 1.
Be careful. Don't just eliminate it and make it not be a fraction. That's still up there. And on the bottom is just the square root of x plus 1 plus 3. Questions on the algebra so far? Am I writing big enough? Can you all see that? Okay, now let x go to 8. You shouldn't have any problems. If x goes to 8, top is 1. The bottom becomes the square root of 9, which is 3, plus 3. 3 plus 3 is 6. So you should just get 1/6. That should be the slope. Now, when we use our formula, y minus y1, well, okay, so this is the slope. What's the point? What's the point we're working with here?
8, 3.
8, 3, right? 8's the x value, you plug it in, you get 3 comes out. So it should be y minus 3 equals 1/6 x minus 8. And you can move things around there. I'm just going to go graph this because I can type it in all like this on the graphing utility. This is going to be y minus 3 equals 1/6 x minus 8. There it is.
So the final answer, the equation would be y is equal to 1/6x plus 5/3.
Plus 5/3. Is that what you got?
That's what I got. Yes, sir.
Yeah, no, that's right. So 1/6 x plus 5/3.
And then that answer wouldn't have a limit sign in front of it, would it?
No, in fact, these are completely separate ideas. The limit is what gives you the slope, right? That's all it does. This is just the equation of a line. That's all it is. So your limit actually stopped. Pay attention, everyone. The limit went away right here. The reason why the limit went away is because you let this x go to 8. And as soon as you let x go to 8, there's no more limit. You're done. Any questions? Give me 5 seconds. Okay. All right, so now when I did this setup for this whole idea, right? What we did first is we picked a point A, and then we picked a second point, which we called X, right? And that was kind of arbitrary. We just picked it. And then what we did is we slid this point on top of that one by letting the X approach A, right? So it wound up being a limit as X went to A. And visually, it was physically moving that X value from here over to the A, right? But that's not the only way we could have done this. There's another sort of approach that we could use. So I'm going to show you that now, and then we'll discuss why in a minute. So another approach would be to do this. Where is it? Here we go. So we could still pick a first point, okay? We could still call this point A. And then we could pick a second point over here. You know, I'm on the wrong picture. Here we go. I wanted this one. Sorry. First point is A. Pick a second point over here. Now, previously we called this X, didn't we? That's what I called it. I called it X. But this time I'm not going to call it X. I'm going to call it something else. if this point here is A, then if I pick a point over here somewhere, wouldn't that be bigger than A? So
Mhm.
it would be A plus something, right? A plus, I don't know, whatever amount I want would move me to the right. So we're going to call this, instead of X, we're going to call it A plus H. So it's this value A, but add something to it, okay? So instead of me saying A and X, I'm saying now A and A plus H. Same idea though. I'd like to now see about moving this over here. So how am I going to make A plus H turn into A?
You subtract
Going-
H.
What's that?
Subtract H.
Subtract H, or just think about what happens as you move over. Isn't H getting smaller? So the smaller,
Oh, so this is gonna be like the difference quotient where you're trying to set your H factor equal to 0 or as close to 0 as possible.
that's right. So what you have to see here is, in order to move this point over, in order to start sliding this point over, what you need to do is make this H value right here get smaller and smaller and smaller. In fact, make it go to 0, right? If H goes to 0, you're going to slide that point over. Are y'all understanding that visually? Now, let's see, how would this change our formula? Because we knew the formula we were using was this: limit X went to A, it was f of X minus f of A over X minus A. That was the first definition I gave you for the slope of the tangent line. That's what we've been using. But if we're going to use this second approach, then the limit is no longer going to let X go to A, because we have no X in the problem. The thing that we have is H. So we're going to let H go to 0. That should slide this point over. And now what changes here? Well, you tell me what changes. Do we have f of X anymore?
That would be,
So what is it? It's X, it's F with this plugged in, right?
yeah, so f of A plus H,
So that's f of A plus H.
then would be minus f
And
of
that becomes the
H.
top left side, and then minus f of A, and then over the X, which is actually A plus H, and then take away A. You'll
So
see what
H.
happens on the bottom?
Yeah, just H.
Yeah, the A's cancel. So you get this. And this will give you the same answer, but it's a different type of limit. So what I'm getting at is, if you want to find the slope of the tangent line to a curve, there are two ways you can find the slope of that tangent line. There are two formulas that you can use. This is the first version that I showed you, and now I've given you a second version. So I'd like to show you how the second version works on the problems that I already did. Okay, so I'm going to do some of the problems that I just did. I'm going to do them again, but I'm going to use the second formula instead of the first. So which one do I want to do here? What was the first one I did? That was the first one I did, right? Right there. So I
Yes.
would like to do the same problem, but I'm going to choose myself to use the second definition. So I have that right here. I'll just copy it. Here we go. So I'm going to use the second definition of the limit of the slope of the tangent line. Now, the good news is that A is still 3. I mean, like, A is the X value, that doesn't change, okay? So the slope of the tangent line here will be equal to the limit as H goes to 0 of f of A plus H. So I'm going to write f of A is 3 plus H minus f of A, which is 3, all over what?
Still be H, but
H, just H, right?
Hmm.
Okay, so this is this. This is that. And now we can actually figure out what those are. So pay attention to this next part. Okay, I need to plug in 3 plus H into the function, right? That means everywhere I see an X in this function, I need to replace the X with 3 plus H. So it's going to be 3 plus H squared plus 3 plus H again. That is just that yellow part. Then I subtract from that f of 3. Now, what was f of 3? I think we plugged 3 into the function earlier, didn't we? We
yeah,
got
12.
Yeah. So that's this part. And then all of this over H. I know it looks different, okay? I know this is like, this looks like a different expression. It's supposed to look different. But we should be able to get to the same answer. So let's see if we do. First thing I'm going to do is check. I want to make sure I have 0 over 0 here. So if I let H go to 0, this becomes 3 squared plus this becomes 3. And then I'm going to have minus, this is just 12. So on top, I get 12 minus 12, that's 0. And on the bottom, H is going to 0, so it's 0 over 0. So I've got to do some algebra. So the algebra I'm going to do is I'm just going to simply, I'm going to expand out the numerator. So that I'm going to multiply the 3 plus H, squaring it, like multiply times itself. I'm going to trust that you can do that on the side if you needed to. 3 plus H times 3 plus H. Well, and you should get 9 plus 6H plus H squared. And then you'll have the 3 plus H here. Then you have the minus 12 here. Do y'all see that the 12, the 9, the 3, and the negative 12 all go away?
Right, you should be left with H squared plus 7H over H, which I would factor down, H plus 7.
So you get now how many H's? It looks like I have 7 H's on top, combining those two together, plus an H squared still up top, all over H. And since both of the terms up top have an H, I can factor an H out and cancel the H on the bottom. And if I now let H go to 0, that goes away and I'm left with just 7. Wasn't that our answer from earlier?
Right, for the slope.
So what do y'all think? Do you think that this formula was easier to use or harder to use compared to when we did it this way? Remember what we did here? We just did this and then we did just a quick factoring and cancel and we were done, right? What do y'all think? First way or second way better? Which one?
I like the first one more.
Yeah, I like the first one. I like the first one. But they both get you to the same answer. And you should be equally willing to use either one. Okay, so what I always tell my students is don't go marry one of these formulas, okay? And be like, that's the only one I'm going to use. You need to be open to being able to use both. And the reason is because sometimes the algebra is easier using one way over the other. So you start to get bogged down, you try the other formula and maybe it'll be nicer. Okay, how about this one? Let's try this one with this new formula. How are we doing on time? Got about 10 minutes? Okay, I'm going to move quickly through this. So I'm going to be using this formula. So here's what I'm going to do. I'm going to take the limit. So h goes to 0. By the way, on that previous problem, I didn't finish the problem because it asked for the equation of the tangent line. I stopped when we got the slope because we already knew how to do it from the previous example, right? So the slope of the tangent line here is limit h goes to 0 of f of, let's see, f of a is 2 here, so 2 plus h minus f of 2 all over h. There we go. That's the formula, which is the limit as h approaches 0. Okay, I need to plug 2 plus h into this function. So that is 1 over 2 plus h squared minus, now I plug 2 into the function, which gives me 1/4. And then all of that over h. Any questions on that? No? You can check for yourself. The top goes to 0, bottom goes to 0. We have 0 over 0. This is bad. We need to do some algebra. What algebra would you recommend I try here?
Combining the common denominator.
Yeah, let's get a common denominator, put these together. This might suck. Okay, here we go. Algebra. I need a 4 down here and a 4 up here. Here, I need a 2 plus h squared and a 2 plus h squared. That sucks. Okay, this is it. I mean, this is my life right now. Okay, I have to deal with it. So when I put those together now, my new numerator will be 4. Take away the 2 plus h squared over the common denominator, which is 4 times 2 plus h squared, then all of that over h. This is looking pretty nasty. Would y'all agree that looks kind of bad? But something good's going to happen here. You see that in yellow? If I go over here to the side and do that, I will get 4 plus 4h plus h squared. If I FOIL that out. So if I rewrite this, watch what happens. I get 4, then that minus sign. Okay, very important. That minus sign is in front of this, right? And if everything here turns into this here in yellow, then every one of these gets subtracted. So it becomes minus 4 minus 4h minus h squared, everything over h. And those 4s go away. And do you see that everything left now has an h in it? All the terms have h. So we should be able to factor an h out.
Wait, where did we?
Oh, wait, hold on. I'm missing my denominator. Oops, sorry. Is that what you were asking me?
Yeah, I was gonna say, I feel like we,
I
yeah.
forgot my 2 plus h. That algebra made no sense. Sorry. All of that over h. Those 4s do cancel though, right?
Mm-hmm.
And now I still have a limit. H is going to go to 0 eventually here. In this numerator, I have h's in both of those terms. So I pull an h out, leaves me with a -4 and a minus h over the common denominator. All of that over h. And what's great about that is this h and this h finally cancel out. And now finally let h go to 0. So no more limit. Here it comes. If h goes to 0, we get -4 on top. And on the bottom, if h is 0 here, You get 2 squared, which is 4, and then 4 times 4 is 16. And that gives you negative 1/4.
That's just our slope, and then we just plug that in and work the equation.
Yeah.
Okay.
So that's exactly what we got when we did it the other way, right?
Mhm.
When we did it this way, we
Yep.
got negative 1/4, and we continue. So I don't know, I would say in the 2 examples I've done so far with this second formula, I would say that both of those, the first formula was probably better, right? Wouldn't you say?
Mm-hmm.
So I'm not going to have time to do this, but I would leave this as an open challenge to you, not challenge, as practice. What about the 2 problems I gave you to work in groups when we did breakout rooms? Wonder if you could do those using the second formula, kind of see what kind of algebra has to happen. All right, we're going to take our break, 10 minutes. I'll put a timer up here. We'll be back and we'll continue, okay? But let's take a 10-minute break. For those of you who are here, I put up a problem. Don't start working on it, just look at it. You're back.
Give me 1 second, sir. Someone just knocked on my door.
Okay. So how's this going for everyone? You all doing all right with this so far?
Yes, sir.
Okay. I think when you get to the homework, you'll see, I mean, it's really the algebra is going to be the thing that kind of hangs you up. I mean, the formula is the formula. So it's just, can you get the algebra to work out so that the limits work? All right, so I put a problem up here for you to think about. All right, find the slope of the tangent line to this curve. And notice I used y equals instead of f of x. That makes no difference. You could look at this as f of x equals x cubed. I'm just trying to get you used to seeing a different notation where you put y instead of f of x. Same, you'll do the exact same procedure. But think about the amount of work this would take, right? I mean, from what we have right now, you're going to have to calculate 10 different limits, aren't you? Because for each one of these, like in this first one, a is 0, right? Then a is 1, then a is -1, then a is 5, and -8, and so on and so forth. And you got to do each one of those, just like we did these, right? So what happens is we get to this point where, like, look, is there a shortcut or an easier way to do this so that I only have to do the limit one time? And then from that, use that to be able to answer multiple questions like this. And the answer is yes, and this is a pivotal point in the class right now, is that we realize that we do not want to do this for 10 different things. So instead what we do is we say, all right, let's find the slope of the tangent line for this curve at, I'll tell you where we're going to do it, at x equals a. And we're not going to fix it as a number. We're going to leave it as a variable. And then we're going to do all the computations and see what we get at the end. So we're not actually fixing a to be like an actual number. We're just going to leave it as the variable a. So I'm going to use the second definition to write down what this would be. So the slope of the tangent line would be the limit as h goes to 0 of f of a plus h minus f of a all over h. Right, that right there is the second definition I gave you. Now for us, we know what the function is, so we can simplify this a little bit. We can say limit h goes to 0. Now let me call on somebody. Is Nadia here?
Yes, sir.
Okay, so tell me what this would turn into for the function we have up here.
Fx to the third plus h.
Okay, so I think what you're doing is you're just taking this and you're just adding h to it, right?
Mm-hmm.
We're supposed to take a plus h and plug it in for x. So replace x with a plus h, and what would you have? Right, like if I asked you to plug, if I asked you to plug 2 into this, right, Naja, you just do 2 cubed. If I asked you to plug in 3, you do 3 cubed. Well, I'm asking you to plug a plus h in. So you're just going to do a plus h cubed, right?
Mm-hmm.
Okay, so that's the top left corner of this. Naja, are you sure you got that?
Yep.
Okay. Keep going. Minus. Now, Naja, what happens if I ask you to plug a into the function? What will it spit out? Bless you.
Thank you. If you could you repeat? Sorry, it cut out.
In the blue here, now we want to do f of a. So plug a into the function, and what would you get?
Just a cubed.
A cubed. Okay, and then all of that divided by h. Okay. Do y'all see the difference between this and having like fixing a to be an actual number? Like if this were 2, then this would be 2 plus h minus 2 cubed. But we're not going to fix the a. We're going to leave it as a variable. Now, if I let h go to 0, right? If h actually went to 0 here, this would turn into a cubed. That would be a cubed. We'd be subtracting, which would give you 0. And on the bottom, h goes to 0. So we do still, in fact, have 0 divided by 0. So we need some algebra. So the algebra that I'm going to do right now is I'm going to go ahead and cube that a plus h. Let me do this on the side. A plus h times a plus h times a plus h. Now, I'm not actually going to do that work. I'm just going to tell you what the answer is. It's a cubed plus 3a squared h plus 3ah squared plus h cubed. So dot, dot, dot. I'm not showing that work. But just make sure you don't do this, because this would be wrong. A cubed plus h cubed. That's not what you get when you cube a plus h. You don't just cube each one. You have to FOIL it all out, expand it all out. So I get a cubed plus 3a squared h plus 3ah squared plus h cubed. That is just this part. Okay, Daniela, what do I need next? What do I still need to put in here? Are you there, Daniela? There you are. Daniela.
Yes.
Okay, so that's the top left of this, right? So I need to
Yeah.
do what on top?
The a cube.
Subtract the a cubed. And then
Yeah.
all of that is over.
The h.
Okay, Daniela, do you see what's going to happen up top? There's something nice up top that happens.
I can factor out. Well, no.
Does anything go away? Does anything cancel out?
The a cube.
A cubes go away, right?
Mhm.
Okay. Now, Daniela, do you see something that can factor out of the numerator? What do they all have in common?
Yeah, I can factor out an h.
Yep, you can pull an h out. So if you pull an h out of all of them, right? So if you pull an h out of each of these terms, the powers come down by 1. So you have no h's here, you'll have just one h here and then just 2 of them here. Now the h is canceled. And that's what we want. We want that h to go away. So now that we're here, let's let h go to 0. So Daniela, Last question for you. When h goes to 0, Daniela, does anything happen to the 3a squared? Is there an h here?
No.
No, so it's still there. Okay, plus now, Daniela, how about the second one? That has an h there, doesn't it?
Yeah.
So if h goes to 0, it kills all this off, doesn't it?
Yeah.
So that's gone. And then what about the h squared at the end?
It's also 0.
0, right? So you have 0 plus 0. So your final result is 3a squared. This is a big deal, okay? Because what we're saying is that if you want to look at the function x cubed, all right? If you're looking at that specific function x cubed, and you want to know what the slope of the tangent line is at x equals a, well, I'll tell you what it is. It is exactly 3a squared. That's what the slope of the tangent line will be, right? So we got 3a squared. So what's the slope of the tangent line here for part A? What would the slope of the tangent line be?
0.
0, because 3, that would be, this is the 0 is the A, so that'd be 3 times 0 squared, which is just 0. Okay, what's the slope of the tangent line here for part B? 3
3.
times 1 squared, which would just be 3. How about for this one?
Still 3.
Still 3, negative 1 squared, that's going to give you 3. How about for part D? What's the slope of the tangent line here?
75.
3 times 5 squared, that's 25 times 3, that's 75. And do you see now that to find these slopes, it's just a bunch of arithmetic, just real quick arithmetic?
Mhm.
Isn't that better? Isn't that more efficient than doing 10 different limits? You'll see the power of doing it in general as opposed to doing it one at a time.
Right. So then is that 3a squared our derivative for the function?
Yes, so yeah, that's exactly what I'm about to tell you right now. Okay, so getting to my notes here. All right. Here we go. So now let's talk about the derivative of a function f at a number or a point a. Okay, so this is going to be a definition. There are two formulas that I've shown you for the slope of a tangent line, right? Here was the first one I showed you, and here was the second one. Both of those formulas will give you the slope of a tangent line, right, of a function. And you can use either one to do it. These are so widely used, right? We use these so much to find slopes of tangent lines. We have a special name for them, and we have a special notation for them. And that is the name of this, okay, this limit, the name of it is called the derivative of the function f at a, at the number a. That's what it's called, the derivative of the function at a. And the notation we use is this right here. That's our new special notation. And since there were two limits, it can either be this or this. You get to choose which one you want to use.
Oh,
The
they're
important
both.
thing is that this new notation is telling you, hey, this tells you, it says, hey, hey, Cruz, find the slope of the tangent line at x equals a. That's basically, when you see that right there, that's what you're doing. You are finding the slope of the tangent line at a. So that's the new notation. Do you see the little apostrophe here? That's actually called prime. We call that the prime mark. So the way you say this is the derivative of f at a, or you could say f prime of a. F prime of a. F prime of a is the derivative of the function at a.
And both of those variants are considered the derivative of a function?
Yes.
F at the number a?
Both
Okay.
of those limits will result in the exact same answer. Okay. All right. So the derivative of a function at A is the slope of the tangent line at A. The derivative of a function at A is the slope of the tangent line at A. The derivative of a function at A is the slope of the tangent line at A. Have you ever seen that movie Fight Club? It's an older movie, but there's a part in that movie where one of the characters, Brad Pitt, he makes the other guy, Ed Norton Jr., the other guy in the movie, he makes him promise him 3 times. He says, "You promise?" He says, "Yes." I said, "Promise?" "Yes." Does you promise? "Yes." He's like, "That's 3 times you've promised me now," right? That's what he says in the movie. I've told you that 3 times. The derivative of a function at A is the slope of the tangent line at A, right? That's what it is. I'm telling you 3 times because I want you to remember that. That should be like hardwired into your brain now. That will be for the rest of your life. That's what the derivative of a function at A means. Slope of the tangent line. That's all it is. Okay. So let's see if you can't wrap your mind around this. This concept. It might be a little premature, but I think you can handle it. This problem we just did, right? What I did, we kind of take a step back and look at it, is I gave you some function f, didn't I?
Right.
And then we found f prime of a, didn't we? Specifically, I gave you x cubed, and you, after we worked this out, we said 3a squared would give you the slope of the tangent line, right?
Right.
So do you remember when I was saying, like, what's the ultimate goal of this class? One of the main goals of this class is that if we have a function that's doing something weird, that we would be interested in knowing the highest and lowest points on this graph.
Your mins and maxes, yep.
So isn't that when the slope of the tangent lines would be 0, right? And couldn't we then determine that? Because doesn't this formula right here give you the slope of the tangent line? So if you wanted to know at what values of A, question mark, what values of A would you actually have flat tangent lines? All you would have to do is take this and set it equal to 0 and solve it, right? And if you solve that equation, then you now can tell me exactly what x values correspond to flat tangent lines. So big picture, I hand you a function and ask you where are its highest and lowest points. One of the things you're going to do is take the derivative, find the derivative, and then set it equal to 0. That's the big picture where we're headed. We're not quite ready for that, but I want to start getting that out there now, because the sooner you start to wrap your mind about how special this is, you'll see how we're going to use it later. Okay. So let's do another one, like an actual example. So if f of x equals 1 over the square root of x plus 3, find f prime of a. So I'm asking you to find a formula that's going to spit out the slope of the tangent line for this graph at any arbitrary value of a. That's what I'm asking for, right? So I have 2 definitions I can choose from. I can choose from the limit, the first limit I showed you today, or the second one. I'm doing the second one. Now, there's a reason why I'm doing the second one. It's to lead us into the next section, but you could use both. I told you not to marry one or the other, but the second one's going to be used more. So Let me just write down the definition. This is the actual definition. This is what f prime of a is, right? That's the definition of f prime of a. So this becomes limit, h approaches 0. Okay. Alejandro, are you here?
Yes, I'm right here.
Okay. How's this going, Alejandro?
Makes sense so far.
Okay. All right. I'm going to ask you to help me fill this out. So tell me what f of a plus h is, and here's the function f of x up here.
Let's see. Would it be 1 over x plus 3 cubed? Or I guess the square root of
The square root of
x plus 3.
what are you plugging into the function? This is the original function, right? I'm asking you to plug what into it?
Oh, a plus h.
A plus h. So you're going to go in here, you're going to replace the x with a plus h, right?
Yes, sir.
So it'll be 1 over the square root of a plus h plus 3. Alejandro, that makes sense?
Yes, sir.
Replacing, taking a plus h and evaluating this function at that a plus h just means replace the x with a plus h. Then we want to subtract from that. We'll stick with you, Alejandro. What about the next piece? What if I ask you to plug a into this function? What is it? So replace this x with a, which means replace that x with a. And what do you have?
It'd be a plus 3 or square root of a plus 3.
On the bottom, and then up top, you'd have 1, right? 1 over that?
Yes.
I don't like the way I wrote that. 1 over the square root of a plus 3. Then everything here divided by h. Does anybody have a question on this? Plugging in a plus h and plugging in a. So that's, I've asked at least 2 students to do this, and it's kind of hanging people up a little bit, this plugging in. So you want to be careful with this. Make sure you understand we're just evaluating the function at some value, some variable expression. So just replace all the x's with that variable expression. No questions? Oh. Weird. We're okay? I'll take a volunteer for the next step.
I think we're gonna have to find a single denominator first before we can clear
And do
squares.
the conjugate?
Yeah, and then
Yeah,
you'll
so
go
square
conjugate.
roots, you should be thinking conjugate. Definitely be thinking conjugate because you see square roots. The problem is, though, that before you do conjugate, you have to put these two together. So you have to get a common denominator. This is going to be ugly. Go ahead, Bree.
Okay, so you're going to multiply the first fraction by the square root of a plus h plus 3 on top
Just
of
a plus 3. Just square root of a plus 3 because that's what the
Yeah,
other.
that's right. Yeah, the other one you do that. Okay.
Yeah, on the other one, the square root of a plus h plus 3.
Okay. Yeah, that's one.
Look, this is going to be ugly, okay, everyone? This is going to be really ugly when we put this all together. But this is what you have to do, okay? I promised you that the algebra would be a challenge. And I guarantee you that calculus will deliver that challenge to you. All right, so here we go. My new numerator, square root of a plus 3. That's getting sloppy. Square root of a plus 3 minus the other numerator, square root of a plus h plus 3, all over. Okay, so all that is right there is this times 1 minus 1 times that. So it's just putting the numerators together. That's over my common denominator, which is the square root of a plus 3 times the square root of a plus h plus 3. That's the common denominator that we created. And that all of that is over h. Now the conjugate. Now the conjugate. So I'm going to be looking at the numerator, and I'm going to be bringing in the conjugate over here on the top and bottom. And yes, it's going to be ugly. It's going to be the square root of a plus 3 plus the square root of a plus h plus 3 all over the square root of a plus 3 plus the square root of a plus h plus 3. So this problem is a really kind of a challenging problem because you have to first combine the fractions together. That's this step where I'm combining them together. And then after I combine them, now I have to get rid of the square root somehow and do a conjugate. So here we go with the conjugate. Multiply here to here. Limit h goes to 0. Okay, that's going to just give me a plus 3 because the roots cancel. I do not have to multiply the middle ones. I just have to multiply the outer ones. Right? Don't worry about the middle because they're conjugates. Now, careful here. What do you get when you multiply this green times that green? You have to be real careful with this.
You're gonna get a negative.
You get a minus because one's positive, one's negative, so I get a minus, and then what's actually here?
Minus a, minus h, minus 3.
Yeah, so it's all of this, right? A plus h plus 3, the square roots go away, but you're subtracting all of them. So I'm going to go, Cody, a little slower. I'm going to go a plus h plus 3, but it has to be in parentheses because the negative sign must distribute to each one of them. Now look at how bad the denominator is right now of this. It's this times all of that. So I'm not going to multiply it out. I'm just going to leave it. But then all of that is over h. So in terms of algebra, this is about as sticky as it gets right now when it comes to limits. This is about as bad as it gets. Combining fractions, conjugate, all mixed into one problem. But really, really nice things happen right now. Do y'all see what happens up top, in the very top?
Yeah, you're left with just a negative h.
All of that goes away except negative h. And then that h there cancels with that h there. So the a's go away, the 3's go away, you're left with negative h, and then the h here and here cancel, which means that we are at limit h approaches 0. I have a negative 1 on top, and then over this nasty thing. When the h is canceled is when I'm happy, because when the h is canceled, that means on the next step, I should be able to run the limit. I should be able to let h go to 0 now. So I'm going to let that h go to 0 and that h go to 0. And let's be real careful and see what we get here. No more limit because I'm letting h go to 0. Negative 1 on top. Okay, I have square root of a plus 3. Nothing happened to that first one. Nothing happened. This one, the h goes away, so you get another square root of a plus 3. Then in parentheses, you have square root of a plus 3 plus This one, the h goes away, so you have another square root of a plus 3. Now that could be your answer, okay? That we could leave that as the answer, but we can actually clean this up. This is a plus 3. That's those two together right there. These two multiplied, the root goes away. These two are being added together, so I'm going to say times 2 of the root a plus 3s. And this will be my final answer, and then we'll talk about how I got it. So 1 over 2 a plus 3 to the 3 halves. To the 3 halves is my final answer. How did I get a plus 3 to the 3 halves? What did I do?
Wasn't it a plus 3 to the third power with a square root?
Mm-hmm.
Because you
So I
put the a
took
plus
that,
3.
which is to the first power, and this, forget the 2 for a minute. That's the same as a plus 3 to what power?
2.
The square root.
Yeah.
Means to
1
raise
half.
it half power. And now the
Yeah.
2 I have here, let's just put the 2 out front. So if I ask you to do something to the first power times the same thing to the half power, what do you do to these exponents? So if I ask you to do x squared times x cubed, how many x's is that?
5.
You added them, right? So you need to add the exponents. 1 plus a half is 3 halves. And that gives you this answer. Okay.
So is the square root always raised to like 1/2?
Yes.
Okay.
Mhm. The square root of x is x to the half. If you want to go more general than that, the nth root of x is x to the 1 over n. And if you want to go even more general, then x to the m power, the nth root of that is x to the m divided by n. That's really the big daddy one right there.
Okay, thank you.
Okay, well, that took a little while, didn't it? I think there's probably a couple of places you could make mistakes there, would you say? Lots of places you can go off the rails. Okay, but end of story is this. For this function, we can now find the slope of the tangent line at any point by just plugging that a value into this formula, and we will have it. Now, it took us a lot to get to it, but we got it, okay?
And so in like the homework or like the textbook, was this question got from the textbook? Like, is there like more questions similar to this to like be able to practice a very difficult question, I suppose?
There's going to be a mixture. There's going to be a mixture of problems in the homework. There's one similar to this in the homework. Yeah. Okay. So think about this just for a moment. Here's a function, right? Do you think that that function ever has a tangent line that's horizontal? In other words, when you graph this, whatever it looks like, do you think that there's any places where we have maximums or minimums happening? Just what's your instinct tell you? Just looking at that, yes or no?
I want to say no, because isn't that a reciprocal graph or a reciprocal function, which is kind of.
Yeah. Maybe because it looks like a reciprocal. But would you at least agree that that's not something that you feel confident by just looking at it saying yes or no?
Yeah, right. I'm questioning it just by looking at it like,
Yeah. So I can tell you no, not right off the bat, but I can tell you that there is nowhere on this graph where you have a flat tangent line, never. And here's how I know. Look at the derivative. Could that ever be 0?
No, because even if you put 0 into it, you're still going to get 6 to the 3.
So
Okay.
yeah, this brings us to a bigger question. If I have a fraction equal to 0, The only way that a fraction can ever be 0 is if the numerator is 0. Let me say that again. If you ever have a fraction, the only way a fraction can be 0 is if the numerator is 0. And if you don't believe that, let me just convince you by multiplying both sides by b. If I multiply both sides by b, I get a is 0. So to solve the equation a over b equals 0, all you really have to do is solve the equation a equals 0. So when I look at this, this is a fraction, isn't it? Can that ever be 0? Well, only if the top is 0. But the top is -1, and -1 won't ever be 0. So just by looking at the derivative, I already know that if I graph this, you will have no you know what I'm trying to say, tangent lines. So I'll do this, I'll graph it. Y equals 1 over the square root of, what was it, x plus 4? Was it x plus 3? X?
Oh, no, the derivative we had, it was
Oh,
-1
no, the
over.
original function.
Oh, the original. Yeah, it was
Third
1 over the
x.
square root of x plus 3.
Yeah, there it is. So there's the graph. Nowhere on this graph are you going to find a flat horizontal line. It's not, sorry, a flat or a horizontal tangent line. Never. It's not going to be there ever. Okay. All right. Let me get back to my notes. All right. The derivative f prime of a as an instantaneous rate of change. The derivative f prime of a not only represents the slope of the tangent line to a curve at a number a, it also represents what's called the instantaneous rate of change of the function at a. So I'm going to give you a slightly different kind of way to look at this. Let's say that you have a graph where this x-axis represents time, and let's say this represents temperature. So maybe you're looking at the temperature outside for the day, right? You know what? We might be able to do this, might be kind of fun. Let me see. Why is that not wanting to leave? Go. Go. Let's look at the temperature. Just going to look at the last few days in temperature here. Okay, so there we go. We've got a graph that basically represents the temperature over the past few days. Let me grab the y-axis here. These are actual temperature readings at my house. So I have a thing outside that keeps track of temperature. So the important thing is, let's just imagine, let's smooth this out. Okay, this is looks like a polynomial function, right? And so this is time, and this is temperature. So obviously the sun comes out, temperature goes up, sun goes down, cools off, up, down, right? Well, if I go to some specific time, point in time, okay, whatever it is, and go here and find the slope of the tangent line, the slope will be a number, won't it? It'll be just some number. And in this case, it would be, let's just guess that it's 8. Okay, I'm just making that up. Okay, that's 8. Pretty steep positive number. Now, slope is always rise over run, isn't it? Rise divided by run. So when we talk about rise up and down, that's a measurement of temperature. So this is 8 temperature here divided by run, which is time. I should put here instead of temp, let me put degrees, because that's how we measure temperature. And time, time's not measured. It doesn't show it here, but I'll just say this is per minute. Okay, I'll just put a unit on here. So what that 8 would represent is at that instant in time, it would give me how fast the temperature was increasing or decreasing at that instant. It's an instantaneous rate of change. It's not an average rate of change. An average rate of change would look like this. I say, okay, what's the temperature here? What's the temperature here? And then I take the slope going through those 2 points. That's a secant line. That would give me an average rate of change, where the derivative gives you the instantaneous rate of change. And you could do this for any 2 quantities. It does not have to be time and temperature. It can be, let's say, let me try and think of something else off the top of my head here. Time is always a good one, but how about, yeah, I'll just do time again. Time. Yeah, let's go time and distance here. You're driving your car, right? You start driving your car, start the clock. You're going to travel in your car. At the end of some time, you're going to have a distance that you travel. So if you go to any particular point, A, whatever it is, go here and find the slope of the tangent line. That slope will represent your instantaneous, what? In this case, I'm going to make this number up. Let's say that was a 4. It would be the distance over time. How do we usually measure distance when we're talking about driving?
Miles.
Miles. And then how do we measure time when we're driving in the car? Miles per hour, right? Something like that. So this would tell you the slope of the tangent line would give you instantaneous speed at that point. And you could be in a chemistry class. This could be like temperature and some chemical reaction. You could be trying to figure out where it was going up and down, how fast it was going up. The key is that it gives you an instantaneous rate of change, not an average rate of change. That's what calculus allows you to do. All right. So that's what this note is saying. It's just saying that the derivative, it is the slope of the tangent line, but it can mean more than that depending on like the framework of where the function is. Now, if your function is some curve that represents linear displacement, in other words, it represents a distance you travel over a given amount of time, then the derivative will always represent the instantaneous velocity of the object. So if this is distance and this is time, and you pick 2 points, or sorry, pick a point somewhere on here, then the slope of the tangent line at that point will give you your instantaneous velocity at that point. So think about this car here. Think about that this is a car. At a certain time you take off, okay, it's going to be 1 hour here that we're driving. So time is measured in hours. So at 1 hour, we've gone roughly about 10 miles. Can you all see that in the beginning of this trip? Right about, let's say, right about here. Do y'all see that the slope of tangent line is very shallow, not very steep? That means at this point during the trip, you're not traveling very fast because your instantaneous rates of change are always small. But as you move further into this trip, you can see that at the end of the trip, you were going faster because your instantaneous rate of change, the slope was greater. And so that's the correlation for that last note, is that if your original function is a position function, your derivative will always represent velocity. Okay, that's the big takeaway there. All right. What time is it? Are we done? Wait, we're not done, are we? We have another hour. Okay.
Whole nother
We're
hour.
done, but we're not done, right? All right, that's it for 2-1. It took us a while to get through 2-1, but that was important stuff. Make sure you do your homework for 2-1. Don't skip anything on that. And if you have questions, which I'm sure you will, please get with me in my office hours. All right, y'all ready to move on? Deep breath. What makes this challenging is that because it's a summer class, I'm covering so much ground today that this next little bit is probably going to be a little confusing. So let me try and formulate it this way. If you look at what we've done today in class, we started with the function, right? And we've learned that there's this thing called f prime of a, which is the slope of the tangent line, right? And I gave you two different definitions for this, the first one and the second one. And I've been really keen on using the second one more than the first one. And the second one that I've used looks like this. Limit h approaches 0, f of a plus h minus f of a all over h, right? And we've seen today that when you do this, okay, when you actually calculate this, you get something here that has a's in it. You'll agree? I mean, we've done a couple of these. Let me go back. We did this really, really nasty one, but we did this one. This is the first one we did. And we got 3a squared, and that wasn't so bad. But then we did this really, really ugly one right here, where I gave you a function, we found f prime of a, and we got this rather disgusting looking expression, but it had a's in it, right?
Right.
Okay. So it's almost like we started with the function, right? We started with the function. We did something to it, right? We did this limit. And then what happened at the end was we got a new function. Right? It's like we started with some function. We did this thing called the derivative. And then at the end, we got this new function that had a's in it, right? So why did I use a? Remember when I was drawing, I said, we're going to have this anchor point. We'll call it a. I could have called that anything I wanted to call it. I could have called it Q. I could have called it R. I could have called it T. I even could have called it X. And if I do change it to X, which I'm about to, how do things change? If that becomes an X, all that changes in this formula is X here and X here, right? Instead of A's. And then our answer will have what's in it instead of A's?
X's.
X's in it. And so it's like we start with a function, right? We start with a function of X, and we end with a new function that is also a function of X. Start with a function of X, do the derivative, end with the new function of X. See if I can. So we did this one, right? F of X was X cubed. We did the derivative of that, right? And we got what? 3a squared, right? Isn't that what we did? What I'm saying is we didn't have to use a. We could have used an X in there, and then our answer would have been what?
3x squared.
X squared.
Right? I would like for us to see that this function of x that we started with is just a function we could graph, right? And the answer we're getting is also a function we could graph. And I'd like for us to graph them together on the same grid, and let's look at what they tell each other, what we can determine from looking at them. So here it comes. Here's the original function. Y equals x cubed, okay? Now I'm gonna graph y equals 3x squared. So what does the blue one say about the red one? Let's see if we can't figure this shit out. All right, so let's say, look at the red one, go to the value 1, go up here like this, and we should be able to find the slope of that line, right? Can somebody tell me what the slope of that line is going to be at 1?
3.
Where are you getting 3 from?
I plug in the 1 into the equation, or I just look up
1
at the blue
into
line.
the derivative, right? To the
Yep.
derivative.
Mhm.
And you get 1. So in other words, the slope of this line, the slope of that is 3, but that corresponds to, isn't that exactly the
Yep.
y value of that blue curve?
hmm
So the y value of this blue curve course at 1 corresponds to the slope of the tangent line there. You'll see that? This is one of those things where it's like a light bulb. It either is going to be on or off for people. They either see it or they don't. Let me do another one. If we do, let's pick another point. How about we pick, it's kind of a crappy function to look at for this, but I'll try it. Let's go with 2. Okay, so if I go to 2 and I go up here to the red curve here, and I want to know the slope of that tangent line, the slope of that tangent line will be equal to what?
12.
12. Now you're getting that because you are just taking that 2 and plugging it into the derivative, but on our graph, it's this y value right here, right? It's that y value right there. I hope you're making the connection, because I'm about to do something you're not going to like. I'm going to take the original graph away. And I'm going to tell you right now that that's the derivative. Okay, so what you're looking at, everyone, is the derivative of some function. Okay, the red one.
So
I want you to draw me the red one now. So act like you never knew about the red one. And I give you its derivative. Can you draw me the original function? It's going to be hard, but we should be able to do it. Now, it won't be a perfect picture, but it will be. We'll get the flavor of what f looks like. So the question here is, sketch f for me. If this is its derivative, sketch the original function. Okay, that's going to be our task. Now, this is a hard one to start with. Okay, so what I think we should do is take a step back and I do the same sort of idea with an easier graph, like an easier thing. And then we'll get back to this one because I think I'm throwing you right to the frying pan here. So what I'm going to do now is I'm going to sketch for you the derivative of a function. So here comes the derivative, okay? Let's say that this is 1, 2, 3. Let's say 1, 2, 3. That should be enough. So here's what it looks like. I'm going to draw the derivative in green. That's an open hole right there. Okay, right there. I'm telling everyone now, what you see in green is the derivative of something. I want you to sketch the original function. I'm going to let you think about this for about 2 or 3 minutes. Okay, and see if you can come up with it. If you can't, I'm going to go through it, but I just want to see if you can make the connection without me showing it to you that first time. 2 or 3 minutes. Okay. See if anybody was able to deduce this. I'm going to ask anyone to respond to this. To the right over here, what can somebody tell me about the derivative of the function? What is it equal to? No?
It approaches 2.
It's 2, right? It's 2 because that it's up, it's constant, it's 2. So that means when I draw the original function to the right of 0, it should always have all the tangent lines should have the same slope of 2, right? Everywhere you are. So what is it? What does the picture of f look like then? If it always has the same slope?
It's just a horizontal line on 2.
It's a line, but it's not horizontal.
Oh.
It always has the same slope though.
So
What's the
straight
slope
line,
have to be?
slope of 2.
2, right? So that means I could watch me draw this. I could just draw, let's see, rise over run, up 2 over 1. 2 over 1. I went up 2 over 1, up 2 over 1, up 2 over 1.
Oh, I see.
Do y'all see that if I go to any point, pick me any point, I don't care where it is, and I go up to the red one, what's the slope of the tangent line here going to be? 2, right?
Mhm.
No matter where I am. Slope here, 2. Slope here, 2. Because it's a line, it has the same slope all the time. That's why its derivative looks like this. What about the left side? What's the slope of the tangent line always look like?
Negative 1.
Negative 1, which means it could also be a line, right? With the slope of
Down 1.
down 1 over
Yeah.
1, right?
Yep.
So how about I just draw this? So if I go to any x value over here and say, what's the slope of the tangent line there? It's negative 1. Here, negative 1. Here, negative 1. No matter where I am on the left side of 0, I have a constant derivative. Okay, I think this might be too much of a stretch just by the look on some of your faces, which is why I'm glad we have cameras, okay? Because at least I can get that sense. So I think we'll have to go a little bit slower. Hold on. Let's try this a slightly different way. All right. I want us to just kind of clear your mind for a moment. Okay. And I want us to just think about this in a slightly different manner. What you're looking at here is a function f, not its derivative. Okay. This is the original function f. And I want us to discuss what its derivative looks like. So let me pick a couple of key points. Right here at this point, Cruz, are you here?
Yes.
Okay, Cruz, at that point that I just put there, right there, can you tell me what the derivative is there? What's the slope of the tangent line at that point?
-3.
I think what you're giving me is just the y value of that
Is it
point.
0?
Cruz, do you see, there's a tangent line here, right? You see that?
Oh, okay. I see.
Okay, so what's that slope? What's the slope of a horizontal line?
Then it would be 0, like Brian said, wouldn't it?
0, right? 0. So if I were to look at the graph of the derivative at this value, the derivative would have to have a value of 0. So I'm going to put a 0 on the y-axis. I'm going to stick with Cruz. Cruz, over here, what's the slope of the tangent line at this point? We're at the bottom of that.
It would be the same, wouldn't it?
0, right? So the slope here is
It
0.
would be the same 0. Yeah.
That's right. We'll have a 0. The derivative is going to have a 0 here. Cruz, there's one more point where this happens. Do you see it? Right here. At that point right there, the slope of the tangent line is 0, which means the derivative also would have to be 0 here. Is everyone clear with those 3 points? What we know is that the slope of the tangent line should be flat, which means that the derivative should have a value of 0 at each of those points. The more interesting question now is what's happening between here and here. So I'm going to stick with Cruz because I think Cruz is going to get this. Cruz, generally speaking, between this point and this point, if you were to pick any value you want, okay, so I'm just going to pick one for you. Here, the slope of the tangent line, you're not going to be able to give me the numerical value, but can you tell me if it's positive or negative? So look at that tangent line. Does that look like a positive slope or negative?
Positive.
Positive, right? And wouldn't that work for any point you pick? Any of these points that you would ever pick, Cruz, aren't these always going to be positive slopes? At least over here between here and here. Yes?
Yes, because you can see it rising right there.
Yep, it's just rising up. So we have positive slope. That means the derivative has to be positive. In between these two values, here and here, the derivative has to be positive. So if I were to graph the derivative, Cruz, it would just have to be something that looks like that. See how every point on the blue is positive? It's above the x-axis. Okay. I'm sticking with Cruz. Cruz, on the other side, between between this point and this point, if you were to pick points here or here or here, what can you tell me about the slope of the tangent lines here?
Well, this one's going down, so this one would be a negative slope.
Negative. Good, which means that the blue function between those 2 points should be negative, which means it should be below the x-axis when I draw it. And so it should go down like that and connect back. So what you're seeing in blue is a graph of the derivative of the original function. Okay, good, Cruz. Sorry to pick on you the whole time. I really felt like it would be better if we just stuck with one person on that. Okay, I'm going to clear this out and then I'm going to show it to you animated. It's a little different animated. So I'm going to move the point across here, okay? And I want you to just pay attention to the slope of the tangent line as I move it across. So right now, the slope of the tangent line is negative. Now it's positive. Now it's negative. Now 0 and positive, right? You see it just kind of tracing along here. So if I were to actually take the value that's coming out and plot it. Okay, so watch as I move across here. Pay attention to this slope right here is 1.88, and I'm plotting that as a point up. It's 1.88 high. So as I move across, it goes up. It's still positive, but it's coming closer to 0. Now my green dots have to go below because the slope is negative, and then back to positive. And so if I put it all together, I get the graph of the derivative. Kind of what I did in blue a second ago. Okay, I hope that makes sense. Let's take a look at another one. What you're looking at is a function. Here it is. It's actually the function 3x. Can anybody tell me what the derivative is going to look like here?
Is it just going to be 3?
3. Look, this is a straight line, right? So no matter where you are on this line, the slope of the tangent line is always 3, right? Here it is. Look, you can kind of see the green little slope there. It never changes. So if I were to try and draw the derivative should always be the value of the slope, which is 3. So it's just constant. So the red is the original function. The green is its derivative. As I move from left to right, look at the derivative. The derivative is negative, 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 then 0, then positive, 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 right? Negative, going through 0 and turning to positive. Something like this. Negative, because it's below the x-axis, going through 0 and turning into something positive. The thing that students have, I think, the most trouble with is making the connection that the slope of that is the y value of this. So the slope of this line, tangent line, is equal to the y value of the derivative, the output of the derivative function. I'll give you another one. I'm going to open this. Well, let me ask Justin. Justin, are you here?
Yes, sir.
Okay, Justin. Is there anything, just look at that. Imagine Justin moving from left to right and think about the tangent line. Is there anything kind of unique that you can tell me? Anything about that that just looks, is there anything?
I feel like the slope would be similar on both sides of the y-axis. So it would kind of look like a parabola.
So tell me right now as I move through here, slope is, you just tell me positive, 0, or negative as I move. Okay, you ready? So what am I right now?
Positive.
Okay. Oh, I don't want to show it. Okay. Then
Still positive, approaching 0.
Approaching 0, gets to 0, and then what?
And it'll be positive again.
Positive, small positive, right? But then getting bigger and bigger positive, right? So let's go through this again, Justin. Big positive, right? Big, big, steep positive. And then it's kind of shallowing out, still positive, but getting smaller, and then getting to 0, and then goes back to positive and stays positive. And that means it looks like this. Big positive, right? These are big positive values. Approaching 0, getting to 0, staying positive, and going back up to big positive. Justin, does that kind of make sense?
Yeah, it does.
Okay. I've got more. These are fun. Okay, how about this? Jorge? You here?
Yes, sir.
So is this making sense?
It's a little conceptual for me.
Yeah, I get it. Okay, so look at the tangent line here, Jorge. Just tell me, I'm going to move from left to right. Just tell me if you can tell from looking at this graph whether or not the derivative, the slope is positive or negative right now.
It's a negative right now.
Negative, right? Okay, is it a big negative number or small?
Small.
Small. Okay, now what happens as I go to the right?
It's getting bigger and bigger.
Bigger, but still negative, right?
Yes.
And then when I get here, it like freaking freaks the hell out, doesn't it? Because
Yes.
you've got an asymptote. So when I get way down there, that's a huge negative number, isn't it?
Yes.
Okay, so I'm going to go back. Let's back up. So Jorge, let's start drawing the derivative. You said the derivative to start has to be small negative numbers, yes?
Yes.
Okay, here it is. Do you agree that that green has little small negative numbers?
Yes.
Okay, and what's going to happen as I start diving down?
Bigger and bigger.
You really start getting to be big negative numbers. Now, what about the other side, Jorge? Let's get to the other side of 0. Jump over there. I'm going to come in from the right this time.
Mm-hmm.
Oh, shit. I lost it. From right to left. So right now we have very what?
Negative or small negative.
All negatives. And as I get closer to 0, moving from right to left, those are going to be what?
Positive.
Are you
I
positive?
mean, no, negative. Sorry.
Still negative and real negative, really big negative. Yes?
Mm-hmm.
Okay, so let's put it all together. If we were to graph its derivative, it would be, like Jorge said, small negatives getting to be big negatives. And when we get to the other side of 0, we're going to have big negatives getting to be smaller negatives. And so the green is the derivative of the red function. It's conceptual. All right, here we go. Square root function. So I'm gonna actually start it out right here. And let's go to, is it Bree? Yeah, it's Bree.
Yes.
Okay, Bree. All right, so from where I have that dot right now, the derivative is what? Positive or negative?
Positive.
Okay, if I move to the right, what's getting
if you're moving, yeah, it's gonna get bigger.
bigger?
Your y values.
The y value is getting bigger, but what's happening to the slope? What's happening to the slope of that green?
Oh, it's getting closer to 0, I guess.
Yeah, it's flattening out. Now it's positive still, right? It's positive.
Yes.
It is pitched up a little bit. So Bree is saying as we move to the right, our derivative should be positive, but actually getting smaller.
Yeah.
And Bree, what about if I go to the left? Am I going to have positive still?
Positive what?
Positive slope.
Oh, yeah. If you're going to the left.
Yep. As I'm moving this way, I still have positive slope, right?
Mm-hmm.
Now, as I start to get here, what happens? Oh shit, right? What's happening? Oh shit, right? It's starting to turn, it's still positive, right? But bigger and bigger values.
Yeah.
Until I get to actually 0, it becomes infinite. It actually turns completely straight up.
Straight up.
So let's draw the derivative. Let me just show it to you. Here's the derivative. See if it makes sense. As you move from left to right, initially the slope is almost vertical, which is why your derivative is huge positive numbers. But as you move to the right on the red function, those tangent lines start to flatten out. So that means the derivative starts to get closer to 0.
Yeah.
This is weird, y'all. I know this is weird, like when you're first seeing it, making these connections. Let's do this last one. Sine of x. All right, Bree, you're off the hook. Brian, you're up.
All right, let's go.
Okay, so all right, Brian. I'm going to start you out here on the left.
Mm-hmm.
Okay.
So we're starting off at we're starting off positive, then we get the 0.
Okay, we get to 0.
And then we start going negative.
We're at negative derivative, right? And then
heading towards 0.
and then back to 0,
And then heading back up,
positive,
and then hitting 0 once again,
0 again,
and then going negative,
negative, and then
and hitting 0 again.
0 again. Okay, so you've got this thing that's going to be, let's recap. You're going to have like 0 that's going to be negative for a while, and then 0 again, then positive for a while, then 0, and then negative for a while, and then 0 again.
Wouldn't it just be the cosine function of that?
It actually is exactly going to be the cosine function. We don't know that, but that's what it looks like. See, like Brian said, when we were here, it was 0, and then as we moved to the right, it was getting negative, negative, and then, well, let me just bring back. So we were at 0 here. See the x-intercept on the derivative right there? Everyone see that? That's a little x-intercept. That corresponds to the fact that that's flat. And then as we move to the right, negative pitch means our derivative has to be below the x-axis. Start to get back to flat, back to 0 on the derivative. Now positive pitch, then back to 0, and then negative pitch, and then back to 0. All right, like I said, this stuff's like a light bulb, okay? It's either going to be like a click yes or no. On your homework, what they're going to give you, the good news is on the homework, what they do is they give you a bunch of graphs of f and a bunch of graphs of f prime, and you're supposed to match which f goes with what derivative. Does that make sense? It's like a match and play game where you try and figure out which goes with which. Do the homework. Hopefully, it'll start to become a little more clear after you do that. See if there's anything else I want to say on that before I move into the next part. All right. So formally, I need to just make sure we understand this, that if you write given, let's say given f prime of x is the derivative of f at x. So again, we're using this new notation and we're not using the a anymore. We're using x. We're replacing the a with x. So if someone gives you a function, f prime of x is the derivative of the function at x. For example, we already seen this, that if f of x was equal to x cubed, we know that the derivative of that is equal to 3x squared. Remember, it was 3a squared, but we replaced the a with x, right? All right, now we get to the rest of the notes here. Can I move on?
But just for clarification, but basically derivative is just saying at any point in this function, you can run the number through this formula and it's going to give you the slope of that tangent spot.
That's exactly what it's saying. For any function, if I want to know the slope of the tangent line at any point on this function, like let's say I want to know the slope of the tangent line here at 5, then all I got to do is run that number 5 through this function, and it'll give me the slope of that tangent line for that graph. That's what it'll do. All right. Now, when this class first started, I think I mentioned to you that there were two men that came up with calculus, right? I did mention that to you, Newton and Leibniz. And I told you that they did it independently of one another, and because of that, they had their own notations. They used different notations for this, but they both came up with this idea of the derivative. And so because of that, we have several different types of notation to represent the derivative. So if you're given a function, all right, then we already know what f prime of x is, right? F prime of x is just the derivative right there, right? That we already know what that means. That's some limit that we would have to do. Another way to write that, though, is to write y prime. If you write y with a little prime, that means, hey, you need to go find the derivative. If you write dy dx, that's dy over dx, that also represents the derivative. So these are all equivalent to one another. Df dx over dx also means the same thing. If you put d over dx in front of f of x like this, that means, hey, we're going to be taking the derivative of this function. And then if you see capital D in front of the function, that means take the derivative. Or if you see d with the subscript x in front of the function, that means take the derivative. It's a freaking nightmare. I know. It's all these different notations, right? The only ones that we are going to use in this class on a regular basis are this one, this one, this one, and that one. You won't see this used too much. And this right here, these two are really strictly reserved for when you get to Cal 3. Because in Cal 3, you have functions that involve more than one variable. And because of that, you have to distinguish what variable you're talking about. And so this subscripted x is important. But again, that's Cal 3, that's down the road for some of you, not all of you. Not many of you, actually.
I don't think any of us, none of us are math majors, so.
Yeah.
Well, I think
Some people
Jair
do
is
Cal
doing a
3 still.
minor.
Some people do Cal 3 for engineering. If they want to, they can. Because in engineering, there's a class called engineering analysis. That's a combination of linear algebra and kind of Cal 3 is in there also. And differential equations, sorry. So some people take Cal 3 for the visualization. If you have time and you're an engineering major and you're going to be working with anything in three-dimensional space, which you will be, if you have time, I would recommend you take Cal 3 because it's all about everything in three space. Everything we do in calculus is on a flat sheet of paper. Things don't get interesting till you come out into three-dimensional space, which is where we live, right? So Cal 3 deals with that. Okay, all right, so we've got all these different notations. The notation above, in the notation above, this dy dx, which just means the derivative, is called Leibniz notation after Gottfried Leibniz, one of the co-founders of calculus, all right? Now yeah, go ahead.
I was just saying, is that just like a fun fact, or do we need to know that for like if there's a question that says give it to me in Leibniz rotation or something like that, Jazz?
The way this is going to work is like this. I could now do this. If y equals x cubed, find dy dx.
Okay, so the name doesn't really matter. You're just letting us know, just so we know. Okay.
Oh, you mean Leibniz?
Yeah, like is that ever gonna actually matter or no?
You will probably hear in your, if you get into engineering class, you'll probably hear Leibniz notation. You'll hear that because Leibniz notation is preferred a lot of times because it makes sense. You'll see later why Leibniz notation makes more sense.
Okay.
You don't need to know Leibniz, Gottfried Leibniz or anything like that. You just need to know the notation.
Okay.
All right, so now some definitions. A function f is said to be differentiable at some point A if the derivative exists. So you have to remember that when it comes to a derivative, right, the derivative is a limit. And not all limits exist. We've studied limits that don't exist. So a function can only be differentiable if the limit exists. Most of the time in this class, it will. But that's an important statement because we talked last class about this thing called continuity. Remember continuity? Continuity had to do with the idea of can you draw a function without picking up your pencil?
Right.
If you could, then it's continuous. Differentiable means that everywhere, well, differentiable at a point means that when you go to that point, the derivative exists, that limit exists. So if you're differentiable at a point, you're said to be differentiable at A. If you're differentiable on an entire interval, okay, that means you're differentiable at every point in the interval. Now, this is a nice theorem. This theorem says if you have a function that's differentiable at some point A, then it must be continuous at A. Meaning if you have a slope of a tangent line, if it exists, then your function must be continuous. You must be coming in from both sides to the same place. So differentiability implies continuity. So if you're differentiable, then you're continuous. This brings up something a little more subtle, a little more background, which is logic. I don't know if any of you have ever taken a logic course or will have to at some point. It's important that you, I guess, understand that when you look at a theorem like this, the order of things matters. This is saying if your function is differentiable, then it must be continuous. It is not saying if you're continuous, you must be differentiable. I'll give you an example. Let's say if you live in Texas, okay, I'm just gonna put Texas here. So if you're like physically standing in Texas right now, then do you agree that you are in the United States, physically standing in the United States? Is that true?
Mm-hmm.
You're standing in Texas, then you're standing in the United States.
Right.
Does it work the other way around? If you're physically standing in the United States, then does that mean you must be in Texas?
No.
No. Okay. So when you have, these are called implications. You can't change the order. You cannot change the order. You're not free to do that. This only says differentiability in guarantees us continuity.
Question.
Yes.
So basically you just look at it like differentiable is derivative, and you can't have a derivative without a limit, and you need a limit for a function to be continuous. So you basically have to have a limit to have the derivative, which then gives you a continuous function.
Yes, and the one other condition is that there's no hole in the middle. Okay, so
right.
That's what gives it, that's the continuity part. So yeah, I don't want to get more into that. Well, let me see. I don't know how much.
We got 19 minutes.
Yeah, I know.
Of technical time. I mean, a lot of these people seem pretty dedicated. They may stay after. Bree gave me the smirk of nope.
Yeah, y'all are doing good. So mathematicians asked a question, okay, because theorems are truths, okay? They're truth, they're a true statement, okay? If you're differentiable, then you're continuous. So mathematicians, let me give you an example of something real quick. How about the absolute value function? Okay, look at the absolute value function. This function right here is not differentiable at this corner. It's not, because when you come in from the left, the slopes of the tangent lines are all negative. And then when you get to the right side, all the slopes of tangent lines are positive. So that means at that corner, the derivatives switch from negative to positive very abruptly. It goes automatically from negative to positive. So your derivative doesn't exist. Mathematicians asked, this was a big question. They said, is it possible to draw a function that is continuous, but the derivative doesn't exist anywhere? So can you draw a function where you don't pick up your pencil, but you can't take the derivative anywhere either? So it's nice and smooth, don't pick up your pencil, but nowhere do you have a tangent line, a slope of a tangent line, nowhere. And that was a very hard question for people to answer, and it took many, 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 many decades to answer. But then they finally found it, and I'll share it with you here in a minute. So the question right now is, when do functions fail to be differentiable? All right, so if you're looking at a curve or a function, when would you have not have differentiability? When would you not have a slope of a tangent line? And there are three different cases that you need to know. The first one is at a corner. Like I just said, if you have a corner, the derivative will not exist at that corner. Let me show you why. Remember when I was going around asking people like Roger, where's Roger? Roger here? No, Roger?
That was seamless. Kind of like I was asking people, hey, Roger.
Gabriella, you there?
Yes, sir, I'm here.
Okay. I feel like I called on you already, but no.
No, I was answering a question a while ago and I made a mistake, so we just went over that.
That's
but-
right. Okay, I'm gonna pass you because you did participate today. How about Marissa? Finally, right, Marissa?
Yes.
Okay, so Marissa, back, like I was asking some students a second ago, as I move from left to right, can you tell me on this graph if the derivative is positive or negative? So right now, positive,
Mhm.
positive, still positive. Hold on. Shut up. Hey.
Relatable.
Steve.
Very relatable.
Sorry if y'all can hear that still. Okay, so Marissa, sorry, positive, positive, positive,
Yes.
and then what?
0.
Something's happening here. Look. So Marissa, do you see that as I come in, the closer I get, I'm still positive, right? And then right when I get to the top, it like immediately flips to negative. See that? You go from positive to negative. So let's look at what the graph of that would look like. You said it would be positive, 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 still positive, and then automatically, boom, it jumps to negative. You see that? You see the immediate jump from positive to negative. So can you see that the derivative is broken? The graph of the derivative is broken. And that's why you're not differentiable at this corner, because of this break in the derivatives graph. Here's another example where you can where you're not differentiable, and that's anywhere you have a jump in a graph. Anytime you have a jump in a graph, derivative can't exist. And then the last one is anytime you have a vertical tangent. So let's go with Jair. Is Jair there?
Yeah, I'm here.
Okay, Jair. I'm saying that right? Yes?
Yes.
Okay, Jair. So look, you tell me about the derivative here.
It's positive.
Positive, positive. Getting bigger, right?
Yeah.
Bigger, 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 bigger. And then you see that it becomes infinite. You get a vertical line there.
Yeah.
And what's the slope of a vertical line, everyone?
Infinite.
Infinite, undefined.
Yeah.
And therefore the derivative is undefined. And then when we get to the other side of it, we have positives that are real big and then they get smaller. So if we graph the derivative, here's what it looks like. And so again, the derivative is broken in the middle. So end of the day, what do you need to know? You need to know that there are 3 places a function can't be differentiable. At a corner or a cusp, if you have a jump in the graph, or if you have a vertical tangent. At any of those 3, you are not differentiable. All right, so I'm going to show you now that function I was telling you mathematicians were looking for. It's an example of a continuous function. That means a function you can draw without picking up your pencil, but nowhere does the derivative exist, nowhere at all. So here it is. Okay, hold on, I'm sorry. What the hell? Damn wife's dogs. Blame it on her dogs. All right, so look at this function here. It looks crazy. What it is basically, all right, what it is basically is a function that does this. It's kind of like a sine curve, but if you were to like zoom in and look at this one little section, you'd realize that on that little curve, it's a bunch of like saw blade teeth. So this is really just like a bunch of saw blade teeth. And then every time you zoom in on one of those teeth, that tooth has little saw blades on it.
So it's like
And then if you zoom in
infinite.
on one of those teeth, it has saw blades on it. And there's an infinite number of saw blade teeth on the teeth, on the teeth, on the teeth, on the teeth. Every one is, no matter how far you zoom in. And so you basically have corners everywhere. It's a really weird concept because it's almost like as you're drawing it, your hand is vibrating to the extent that at no point is it ever moving in a straight line. It's always just a bunch of jagged edges. It's a weird concept.
It's like ever increasing and repeating oscillations. It's like the frequency or the period of the oscillation is just forever increasing the closer at it you look.
Yeah, it's really a hard function to explain. If you look it up, it's called the Weierstrass function. Let's see what this tells us. There it is. Okay, that might be a better picture of it. Wikipedia, we can't really take this on faith, but that's a pretty good picture of it. But here's the actual function. This is the actual function. It's not important. Okay, don't worry about this. You don't need to know this. It's basically an infinite summation of cosine functions, which we haven't even we've never in any class you've been in talked about a function that is an infinite series of functions. That's what Cal 2 is about. You do something called in Cal 2 called series. And in series, we study these sorts of things, and that's when it all starts to like become very difficult. But that's what it is. That's the Weierstrass function, and it's nowhere differentiable. Not important, not going to be tested. I just thought it was interesting. Okay, how are we doing on time? 21. We can finish this. This is just a lot of notes right now, and then we'll get into more mechanical stuff next class. So when it comes to derivatives, remember the idea is that if I start with a function, I take its derivative and I get a new function, right? Well, if I have a new function, what's stopping me from doing the derivative of that function? Like a second time. Does that make sense? We have, like we did, f of x was x cubed. When we took the derivative, we got 3x squared. But what about if we just start over and just take that function, take its derivative? Why not? We should get another answer, right?
Which would mean finding the limit of that, right? Using one
Yeah,
of
it'd
those
be another limit of this one though, this time, right? Of this one. Now you do a new limit with that one. So because we can do it, we have to have a notation for it. So when you have f prime of x, that's called the first derivative of a function. If you want to do the derivative of that new function, the derivative of the derivative, that's called the second derivative, and we do 2 little prime marks up there instead of 1. If you want to do the derivative of that one again, that's called the third derivative, and you put 3 little prime marks up there. And you can go forever, okay? Fourth derivative. Now what we do is we stop using the little primes, because can you imagine like the 18th derivative, you wouldn't want to have 18 little dashes up there. So what we start doing is we put the number up here and we put it in parentheses. And that's important that's in parentheses, because if I write this, that means the fourth derivative. If I write this, this means you're taking the function and raising it to the 4th power. Totally different things. Totally different things. So that's why the parentheses is important here. And then the 5th derivative would be, 5 here, and again, you could go on forever and ever. These are all called higher order derivatives. And in this class, what we're going to see is that the first derivative is very important, and the second derivative of a function is very important. Third and fourth, fifth, they're important, but not as important as the first and second. I'll explain what they mean later, not today. Now, this is the notation using primes. If you wanted to do higher order derivatives using Leibniz notation, you use these. This is the notation for these. So I'm going to just show you, because this is subtle but important. See that one right there? to take the second derivative, you would write this down. That means the second derivative. Do y'all see how the 2 here and the 2 here are offset from one another? The 2 here is above the d, and the 2 here is above the x. You'll see how they're kind of offset? There's a reason for that. The reason is because if you write dy squared over dx squared like that, people might think that you mean this. This would mean take the first derivative and square it. That is not the same as this notation, which means take the first derivative and then take the derivative of that. Totally different concepts. So the notation, we offset the 2's so that you don't accidentally think that it's a squared on the top and bottom. It's a subtle notation thing, but we do it for all of the higher order derivatives with Leibniz notation. All right. Last thing I'll say is something I already said last time, and that is if we have the position, right? We did this last class. Last section. If we're given a position function, the first derivative gives us the velocity. Okay, so first derivative gives us instantaneous velocity. The second derivative, okay, so the first derivative gives us instantaneous velocity. The second derivative gives us the instantaneous acceleration of an object. So I have 5 minutes. Please allow me those 5 minutes to try and explain what this is. I know it's a long freaking class, but let me just try and illustrate what that last thing says.
Sorry, I was still writing it down. You said the second
I'll get
derivative
back
is
to it.
what?
I'll get back to it. If this is time and distance, okay, then this would be your position function. If we graph a position function, take some point x, go here, find the derivative, that gives us the slope of the tangent line. If we graph the derivative, like I showed you earlier when we were going around, I was asking people positive or negative, and we were graphing something. If you graph the derivative of that, you'll get a new function over here, and this will be the velocity function. It'll be the velocity. Now, I'll explain why it's velocity. If you take this slope here is rise over run. Rise was distance, run was time, right? So when you take a derivative, you're always going to be taking your y-axis and dividing it by the x-axis unit. So this slope would be distance over time, which would be velocity. That's why we're saying when you have a position function and you take its derivative, the slope of that tangent line becomes your velocity function. So now here's the graph of the velocity, which is time here and velocity here. If I take the derivative of that, so this is the second derivative, I get a new curve, and this is acceleration. The reason it's acceleration is because it's going to be, if I take my tangent line here, it'll be the y divided by the x. And what is velocity divided by time?
Speed.
Well, distance over time is velocity, right?
Yeah.
Velocity over time is, by
distance.
definition, acceleration. And this is why when you're in a physics class and they talk about acceleration, like the acceleration of gravity is what, like 9.8 meters per second per second? Have you all heard that before? 9.8 meters per second per second. It's because when you look at velocity, velocity is distance over time. But then you're dividing that again by time. So there's velocity divided by time. And so you wind up getting time squared because it's a fraction over a fraction. You can multiply by the reciprocal. So you get distance over time squared, which is meters per second per second. Okay. Position function, take derivative, you got velocity, take derivative velocity, you got acceleration. Right? We'll do work with that later. This is just to lay it all out there. Okay, see what you can do on the homework for 2.2. It's a weird section for homework. 2.1 is more important, I'd say, as far as the mechanics. That's it. I appreciate your attention. I appreciate y'all hanging in there. We only have 13 more of these. Oh, is that right? 13?
Yes. It's an 8-week course, 2 visits a week, so we've had 3 classes, so 16
Yeah.
minus 3 is 13.
Okay. All right, I'll hang out for a few minutes if anyone has any questions. Our first test is a week from Thursday.
How many questions will that have, by the way?
I don't know because I don't know how far we're going to get.
Fair play.
It's not.